Welcome to the Estonian Academy of Sciences. It's a beautiful sunny day, and I'm so happy that so many of you have been interested in reliable cryptography. I am Dan Bogdanov. I'm the Chief Scientific Officer at Cybernetica, and I'm also the head of a standing committee of cybersecurity at the Academy of Sciences, also an academician. So this is conference series. Today I can already tell you it's a series because it's the second. Last year we had a first event focused on post-quantum cryptography, and when we were giving the event the title, when post-quantum was sufficiently future then. And I don't think that we can do only bleeding edge stuff throughout the series, so we will try to focus every year on things which are sort of in reach, but not yet deployed enough. So for this year, we went with reliability of cryptography. And the whole goal of why we're doing this is that Estonia is a country which a German cryptography professor once called the land of exotic gourmet cryptography. I think we're, and I've said this often, we are one of the nations that has one of the highest exposures to modern bleeding edge cryptography in its public services. We're just using it quite a lot. We've had the success that we've had, the people, the researchers, the engineers to build it, but now we have to maintain it. It's like building roads. Build a lot of roads, have to maintain a lot of roads. So this event here, in collaboration with the Cybersecurity Excellence Hub in Estonia and South Moravia. South Moravia is in the Czech Republic, for those who don't know. That's the European Horizon Chess project. Then the Standing Committee of Cybersecurity at the Estonian Academy of Sciences and Cybernetica, a three-way co-organization, is giving us this conference today. We are very thankful for the European Commission project and to our Czech partners with whom we've had several years of great collaboration on improving skills and services, both in Estonia and Czechia. So, to lead in the day, why should cryptographers care about certification and standards? I'm arguing that certification is the ultimate form of peer review. If you're a researcher, then peer review is important for you because otherwise you cannot get published. You write a paper, then you send it to a conference or a journal. Other researchers read it. If they think this looks like science, it's novel enough, then you get published, and then your thoughts actually get out there in the world. But that's not where it ends in real world. So for some researchers, yes, they write papers and that's where it ends for them. But if you ever want your research to be used, then often you need some more people to agree that it was good. Just having a paper doesn't always cut it. So standards. Standards, I would argue, is more countries or more organizations coming together and deciding that some research or some technical specification is good enough to be developed jointly and to agree on, maybe for interoperability, maybe just so that we have some things that we decide are good enough, secure enough. And that can also be a dead end. Some standards never get adopted. They get written. Maybe nobody even reads them or buys them. If the industry doesn't adopt them, then it has been possibly a waste of effort. Finally, somebody goes out and builds something. And that's where it gets interesting. It's whether they use standardized technology, standardized cryptography, representations, formats, schemes, math, is pretty much up to their customers in the end. I would say that most organizations know that standards are out there and buying something standardized is good. But obviously some nation states have their own standards as a sort of a sometimes protectionist strategy, sometimes for other reasons. Anyway, if your product gets built and you want to sell it internationally to have a bigger business and you're doing a security product, making a security product, then there is the next layer of peer review is certification. Somebody has to look at what you built and decide that you built it according to all the standards that everybody agreed to. And now they're going to have a look at your processes of engineering, maybe your source code, your designs, to understand that if you had the engineering discipline to actually build something that can comply with this. And this is something we use, governments use, companies use, to decide something is secure. There are not very many places where cryptography certification is mandated. In Europe, one place where it is for certain digital signature, digital identity applications. If you want to build a digital signature device with certain high assurance levels, then the certification requirements are mandated. That's one of the few places. In like civil use, simple services, in like digital services. Obviously, if you go to avionics or any other safety, then certification is paramount. But with digital services, apps running on phones, everything else that you download something and run it on your computer, everything happens so quickly, the turnaround is so fast. How can certification keep up? And who dares to actually start asking for it? So that's one of the questions we are going to tackle here today in what is the process of increasing reliability in the cryptography that we adopt. One of the big challenges that the world is facing is the transition to post-quantum cryptography. Cryptography safe against a cryptographically relevant quantum computer believed to be buildable, maybe. But it is such a sort of existential event if it gets built that we are preparing, even if it is never built, even if the planet cannot amass enough energy to run it, for example, we're still going for post-quantum cryptography because otherwise the damage would be too high. So this is one of the things that is forcing the hands of governments around the world to transition their systems. And yeah, again, if you have built a lot of cryptography, then you have to transition a lot of cryptography. And you have to certify that, see what the standards are, and so on. So this event, the topic of this event has been timed in a way that it works. It happens at the same time that these research projects are creating their results, and it also happens at the time when Europe and Estonia are tackling this change. So, what are the governments and buyers to do? There are regulations coming which would force more things to be certified in Europe. Everybody's worried about this. I believe there are several people in the room who are worried about this. And some of them maybe haven't not made it here yet because they are worried about this in their offices. But the problem is that without an economic model, this will not happen. If the governments don't, or companies don't start asking for certified technology, then it will not be made because certification can be a lengthy and expensive process. Thus, why certify your product if you know that your customer doesn't know to ask for it? So yes, that is one of the challenges that both the vendors and the customers have. In some areas, you need to do this because it's there in your law or in your mandate. Defense is now significantly looking at how to be more certain of secure communications is all the new hardware that Europe is buying and building. But there's a lot of tools in our phones, in our laptops and computers that might need the extra reliability. So there must be an ecosystem of building, evaluating, these cryptographic products. And this is something that we're discussing today. Many countries in Europe already have it. They're large enough. Estonia, with its 1.3 million people, with about, well, Kristjan will later tell you how many cryptographers we think Estonia has a bit of a problem here, because not all of this is to scale. So that's enough for me as an introduction. Now you know what the problem is and what things are that we are trying to solve. So we have invited a number of speakers here today who know standardization, certification, and especially in the domains of cryptography. And the first speaker, I'm very glad to announce, is Erik Vétillard from ENISA, who leads the certification efforts. Erik, please.
Yep. Thank you. So I'm not exactly leading the certification efforts. I'm responsible for the technical part. So, all right. So ENISA has been tasked a few years ago to actually start making certification schemes at the EU level. That was faced with a great success. In 5 years, we made one. Sorry for that. We had unexpected little glitches that I will explain a little bit later. So the first thing I'd like to go on, which is basically the complement to what Dan was saying just a few minutes ago, is that in the end, everything is about the trust. And when you talk about cryptography, this is what people are doing, and when you talk about certification, it's the same thing. But there's something that a lot of people fail to understand, which is that trust, it's not the property of an entity. Something is not just trusted because of something. Trust is a relationship. It's between someone who trusts and someone who is trusted. So the same person can be trusted by some people and not trusted by some other people. And I think this is something very important. So if you look about it, I mean, I have put the formal definition. So it's basically about trusting that someone will behave as expected. So in cryptography, you do a lot of that. Basically, cryptography is a lot about Alice making sure that she's talking to Bob. So, but if you stop at the cryptography level, the only thing you know is that Alice is talking to someone who has Bob's key. So that's the first level. You're talking to the right key. Now, certification and implementation goes into adding another level of confidence, which is now trying to make sure that this key that Bob is supposed to have is actually only in Bob's hands. That it can, the way it is, the algorithms are implemented, make it unlikely that the key that you think is Bob's key actually is in somebody else's hands. So this is something very important. And the last very important thing that people tend to forget is that when you talk about cryptography, about certification, you can build trust, you can add some trust, but creating it is very difficult. If there's somebody that, talk to a person, it happens every day. You go to buy something, you go to the salesperson, and there's this bad feeling. Or you're just not buying because you're not trusting that person. And they can show you how many certificates, whatever they want, you're not going to buy because you don't trust them. And it's the same here. So it's a very human process in the end. So the process you're saying, we do a lot of things, papers, standards, certification, but in the end, it's a human decision. And I've been fighting for quite a while with particularly the people at the Commission who believe that there can be a fully technical process that automatically builds trust. And it does not happen. So once again, we have to be quite humble about all this. Now, when you talk about certification, the second thing that comes to mind after the trust is the problem of assurance. So assurance is a concept that is actually never defined. It's very hard to find somewhere in the standard a definition that says assurance and then something in front. They always talk about level of assurance, but you can never know what it is. So basically, once again, this is about confidence. But here, this confidence, has two different things. One of them is that it is justified, so there is some evidence. The other one is that it's about specified requirements. So it's not just any kind of confidence, it's confidence that some requirements are met and that we have some elements of proof. So this is the basis for certification. If you want to add certification, you simply need to add two things. One of them is that this is done by a trusted third party, typically by some kind of laboratory or certification body, and that at the end, they emit some kind of attestation, which is called a certificate. So you get this little piece of paper that says, this body did this to make sure that the product, service, or process is actually meeting the requirement. Now, the problem is that we try to make some scales. So common criteria has defined some scales, EL1 to EL7. For those who know, the other ones don't bother. It's basically about evaluation activities. It's about, okay, you have to do this and this and this. Then you have another scale, which is the Van thing, which is more about the resistance to attacks. So here you say, okay, you have to resist to this kind of attacks, etc. So here it's more specific. You can do this for smart cards. You can do this for whatever. You cannot have a very generic thing that says, how you deal with that. It's much more difficult to compare. And then when you move from products, which is what common criteria does, to anything else, in particular IT systems, then you get into audit. Because a lot of things are not about actually having a product with some properties. It's about running something day to day. It's about the processes you put in place. Again, the cryptography is only useful if you're able to manage your keys, etc., whatever. If you lose the keys in the process, it doesn't work. So you have to make sure that everything that is done correctly here. And here you can see that in terms of assurance, it's a little bit less precise here. So basically, mostly they use two levels, which is called limited assurance or reasonable. So the limited is about you ask for a number of documents, you check the documents, and if you don't see anything bad, you say it's okay. So it's basically, you ask for something to check it, it's fine. Reasonable, that you ask for a statement, and then you ask for whatever is needed to do this. So you're going to be much more thorough in your analysis until the auditor is convinced that whatever statement is actually right. Once again, these things, there have been several attempts to say, to put them in parallel, whatever. They are very different. You don't analyze products and services or processes in the same way. It's fine. But we need both, and we need also to make sure that they are matching. So having a super high assurance product and then very bad processes won't work, because the product won't allow your keys to be stolen, but can make sure that someone will go and steal your keys from your processes. So now I'm going to tell you a bit about what happens about the certification right now, what we do in the ENISA. So we have one key regulation, which is the Cyber Security Act, which actually regulates what ENISA does, and also the way we define the certification schemes. So based on that, we have developed, or we are in the process of developing 5 different schemes today. The first one is the EUCC, which is the common criteria. This one is the first one and the only one so far that is actually active. So we've had the first certificates. We have some labs that are ready to actually work on that. Then we have one on cloud services, the EUCS. This one has been almost ready for almost 5 years, but it's not ready because mostly of politics. Basically, this issue of trust. So this is not something that we came up rapidly, but this is something where we're still struggling to figure out how we can trust people or not, what levels we need, etc. So this is something very important at this level. Then there's one on the 5G equipment, which is also having some problems with these issues of trust. Hopefully, those will be solved this year, but we're basically stuck on that. Then we started this year, early this year, the one on the digital identity wallet. So this is something that we're doing now because there are going to be some wallets deployed in the coming years very rapidly. And then finally, there's one that we just got the request for, which is on managed security services. So managed security services, this is basically anything from running a SOC to doing some incident response or incident detection or doing pen testing, whatever. So it's a wide range of things, and we're going to have some certification for the companies performing these. All of these things are linked to regulation. So common criteria, for instance, is linked directly to the Cyber Resilience Act, which is actually going to ask certification from more than a few people. So that's going to be another interesting thing coming here. So here we plan to make sure that the people who actually go for a common criteria evaluation can also claim compliance to the CRA, because you don't want to, doing one certification is okay, doing two is becoming painful. So we're trying to make sure that people don't have to do too many things. Then we have on the wallet, of course, it's strongly related to the EIDAS regulation on the identity, which is kind of obvious. Then we have the NIS2 regulation, which covers a lot of things. So it covers in particular cloud services, it covers anything related to communication, including 5G, and it covers also the managed security services. But the trigger for the managed security services is the Cyber Solidarity Act and the creation of a cyber reserve in the EU. And then we have two very interesting things, which is normally certification is not mandatory, but there are two exceptions. The managed security services for the cyber reserve certification will be mandatory, and same thing for the digital identity wallets. Once the scheme exists, it will be a mandatory application for all wallets. So very rapidly here, the way in which we do these kind of things. First, we have, which is what is in yellow, we have a union rolling work program. So this is basically the Commission telling us, look ahead, you may have something to do on this topic and that topic. So as a response to that, which is in green, what we do is some kind of studies, feasibility studies. So we did one on AI, for instance, which concluded that for now we don't need a scheme, we just need to cover AI in the other schemes. So that's more or less the current status. But we also did a study on managed security services, where here we figured out that we need actually a specific scheme for that. Then we get to the red part, which is where we're actually building the scheme. We do that with the support of an ad hoc working group, which is representatives from the industry and also from the member states or EU institutions or whatever. So this is something where right now, this is where the wallet is. The 5G is still at this level as well, and we're soon going to ask, have a call for the ad hoc working group on the managed security services. So if you're interested into that, watch our website. It will come, I think, by the beginning of the summer. And then we get to the level where we have a draft candidate scheme, which is basically we say, okay, we think we're done. Then we have opinions that are required, a public consultation, and then an opinion from the ECCG, which is the 27 member states, represented by their national certification authorities. And once we're done with that, we deliver to the Commission, and the Commission makes it into what they call an implementing act, which is the law. So the scheme actually becomes a law. I would not have done it like that personally, because schemes have a tendency to evolve quite rapidly. So I think that for EUCC it was adopted 1 year and something ago. They already have one update has already been adopted. There's another update coming, and most likely there will be a third one. So basically we're going to go, this kind of law is going to be updated at least yearly. Okay, whatever. So it's not the easiest way into defining a scheme here. And then once we have a scheme that is available, then we need a period of time for accreditation, because of course the trusted third party are themselves certified, which is called accreditation in that case. So it means that they need to go through a few hoops to get there through an independent national body, and these hoops are not that easy, as people realized with the UCC, because they had 1 year to do it, and at the end of the 1 year, I don't think there was a single one available. It came 13 or 14 months later. So yeah, it was a little bit longer than expected, but now we have the first certificates. Something maybe important around the Cyber Resilience Act and certification. So there are some links with the UCC. Something important here is that we have some dates that are kind of going together, which is that at the end of 2027, there's going to be a mandatory application of that. So the products will need to be compliant and to be able to demonstrate it, which for some categories of product will mean that they have to be certified. And in parallel, CC will move to a few new things in the mandatory as well. So what is really important here is that if you're already doing common criteria, you need to be ready to start to adapt to the new rules, and also to do what is needed in order to cover the CRA, which mostly means increasing a little bit your scope, because CRA covers an entire product at a lower level typically than what CC does. So it's not going to be an enormous work, but you need to look at everything, not just the security functions, to make sure that there is no small mistake somewhere. But really, there are also a number of products that are going to need to be certified with some other mechanisms, mostly about making sure that they comply to what are called harmonized standards. So I mean, if you look at the CRA, there are a number of categories. So there's a category where you have to be certified, and another one where you have to have a conformity assessment, but you can do a self-assessment. However, I would like to warn the people who think, oh yeah, good, I don't have to do a certification. No. You have to do exactly the same thing, except you do it yourself, which means that you're more likely to do a mistake. So it's not that easy to actually do the self-assessment properly. And if you don't do it properly, nothing will happen until, of course, you get in trouble and your product gets involved in some mess. And then, of course, the authorities will come back and say, okay, so what did you do? But you didn't do it right. So this is something where I think companies need to be very careful when doing the self-assessment, the fact that they're doing it correctly. And here, there's going to be a big challenge, I think, for the harmonized standards to actually make sure that this is crystal clear on how to do that. And at ENISA, we're working also to help on that. Very small note on cryptography and CRA. There is very little mention of cryptography. There's one related on the items on smart meter gateways. But apparently, looking at the detailed definition, they don't intend to cover other devices. It's just about other devices in the smart meter ecosystem. Okay, so there's nothing really covering cryptography in the CRA, which I think is sad. Because it is an important component. It would have been nice to see that there would be some mandatory actions there. Yet, however, even though cryptography is not mentioned, there are many, many categories which will rely heavily on cryptography. And if you look at CRA, this is all about making sure that your product is well built and that it uses the right components. There's a lot of supply chain issues. So you will need, if you're a cryptography vendor, to make sure that you have the proper evidence to allow your customers to actually demonstrate that they're doing things right. So if it's identity management system, even if it's the identity management system, they will need to demonstrate that their crypto is right. So, this kind of goes back to the crypto provider here. Maybe rapidly, the AUDI wallet, I'll take as an example here. So we have 25 experts. We have a lot of member states registered, mostly because, of course, it becomes mandatory after that, so they're more interested into this. So the work has started in January. We're already making some progress. We are the rapidly arriving at the end of what we call the preparatory work. But as you see, there's a lot of things to be done. Then we do a scheme, then the scheme is transformed into an implementing act. But schemes are very dry documents, so it means that you need to develop guidance. You need to develop a lot of documents on top of it that will actually help people understand what is happening here. And then we need to work with the accreditation because, well, as we noticed already, the accreditation is actually more of a problem than we expected, etc., etc. And hopefully we can do some pilots as well, because pilots are very useful to understand how things are actually working. And then once we're completely done, then we have to revise the scheme, so we start again. So it's basically an endless cycle here. I'm going to skip that. Just on managed security services, we're really looking into, at first, most likely, we'll be focusing on the, I think, incident management in general as a first thing. So the next step would be an ad hoc working group, and the kickoff, I would say that the call should happen before the summer with the start of the work after the summer. Very rapidly, a few things about cryptography. I am not a cryptography expert, so I'm just basically showing slides. Don't ask questions, please. So there's been, around the common criteria, with the SOG-IS thing that was used in Europe, and now with the UCC, there was always some kind of agreed cryptographic mechanisms. So there's a crypto group who developed a revision that was published early May by ENISA on our website. It covers the basic mechanisms: symmetric, asymmetric, random generation, key management, and cryptographic protocol without an S, actually, because it's TLS. Actually, we may need a few more protocols there, but that's hopefully that will come at some point. So most of the changes in the 2.0 are actually about post-quantum. So now we have some approved schemes, part of the agreed mechanisms. So take a look at it. I mean, it's, the document is, it's actually readable. I mean, I read it on the plane coming here, so it's okay. I mean, it's something that, even the non-experts get a feeling of what needs to be done. I think they put the focus on hybrid algorithms. So the idea basically is that we trust a lot the existing algorithms because we have a lot of experience of how they are implemented. We know the RSA, we know the attacks, we know how to protect it, etc. So we have a lot of confidence. Yet we have this quantum problem, so we pair it with another brand new algorithm. These algorithms we don't know as well, so most likely some cryptanalysts or some smart guy with a laser or whatever is going to find a way to create a problem. But it's okay, because we still have the RSA in the... So basically, there's a lot of combinations there, trying to make sure that we keep the security. And also, they upgraded a few things about symmetric and hash parameters, and a few algorithms have been deprecated a little bit, so now you can see that the limit dates for actually using them in certified product is getting very close. Some of them have a 2025 date, huh? So that's getting very close. All right, whatever, I don't know. So we have, take a look at the document if you want that. Now, what happens about certification is that basically, it's a very long sentence where they say that's the only thing we say about cryptography. And cryptography basically said, take a look at this document and use that, because this is what you need. It's also something that is referred to in the PQC roadmap of the EU. All right, and then everything is on our certification website. You can find some information there. Thank you. Yeah.
This is, thank you very much. I learned quite a bit. This is a time for questions now. You have an opportunity which might not happen that often, so please use it and ask questions from Eric. I can bring you a microphone. There's Michal has a question.
Thanks for the presentation. I have a question about the direction of the certification efforts, because how much is the willingness of being independent from the certification requirements from US? Is this that the requirements will be similar or quite different, independent in terms of crypto algorithm and methods, how to evaluate for example, for random generation number and this kind of issues?
All right, so if you pick random generation, that's an easy one, because I'm not sure there's clearly, completely an EU way of doing it. I mean, for those who have been certified, for instance, in Germany, you understand that it's a bit more difficult when you get a random generation certified there, because they have very strict requirements. I think that regarding the US, we don't have any particular reason not to go with the US. I mean, if you look at, for instance, at the UCC, it's a successor to SOG-IS, which was already a European thing. But there is also something called the CC Recognition Agreement, the CCRA, which includes the US, Japan, and many other countries. So we still are in relation with the CCRA, so this is not at all changed. For the other schemes, I think that they are more specific anyway. So there are no schemes that are, say, intended to be reused very easily. I mean, for instance, if you look at the cloud services in the US, they have FedRAMP, but FedRAMP as a scheme, actually, I mean, it's already a procurement scheme. So it's something for federal government, so it's not exactly something that is intended to be used outside. So we have similar things in the EU, so we're trying to do that. We're trying not to be too different, so that's something that we try definitely. No, but I don't think that there was a willingness to actually differentiate clearly now. No.
Also, I will ask about because if the NISA will have the standards for certification and this kind of stuff, so is there any mechanism that the European countries will have to accept this kind of standards, or they might have their own requirements like the German random number generation? So if it's is it a universal solution for whole Europe, or we will have to still struggle with each country's specific requirements?
Yes and no. The idea is that for most products, you should be able to have a single framework, so a single certification that will be recognized everywhere. Now, regarding the German thing, for instance, I mean, they're still allowed to have, protection profiles, for instance, that would be national, of course. So for some particular things, once again, related to procurement. And this is where we have a big difference. When you have something related to national procurement, you can still do whatever you want. You can have your specific requirement. And of course, this will be covered by the certification. And the other thing is also when you move to national security. Anything related to national security is out of our scope. So it doesn't mean that they won't require a CC certification, but if they want to add their own requirements, it's game. That's really the limit. So what we want to do is that the mainstream products, those can be certified at the EU level. When you get into more custom security, it's more complicated.
Yep. Apologies, we'll have the next questions at the breaks. If you look at the timetable for today, then it's cleverly done in a way that there are 2 talks and then there's a nice coffee break. So you can ask all the questions you didn't do here. Thank you so much, Erik. Thanks again. What we also have in the timetable is the kind of structure where the talks are sort of researchy and then possibly less researchy. So now you get a more researchy talk, but it's rather practical still. So I'm super glad to introduce Vasek from Masaryk University, our good collaborator and friend in the chess project. So Vasek, please.
Thank you very much, Dan.
One request. Erik used the word protection profile, and you are about to use the word security target. Can you explain what those are?
I will explain shortly what it is, and if you buy me a beer for every time I mention security target, I will be a very happy man. Okay, it's my true pleasure to be here in the morning and to share with you my background first. I am a retired cryptographer. I don't do cryptography anymore. I don't dare saying that I would do cryptography. And I dare speaking here about this stuff because I did standardization already in the previous century. I helped designing the original common criteria, namely the privacy classes and part of the non-repudiation. And I shall be mentioning here, as Dan asked, security targets a lot. However, I'll be focusing on the point of view how we certify new cryptographic mechanisms, new cryptographic constructions. And I originally wanted to lead the parallel of this talk together with subjective and objective evaluation of beer. Beer is, as we discovered in the chess project, common value between the Estonians and the Czechs, and many other nations share the love for this kind of beverage. However, since it's very subjective, the judgment of beer, I mean, more than cryptography, I decided to stay shy of the beer, and I shall not be hopefully mentioning beer anymore in this presentation. However, I also exercised a lot with one particular friend, and that is the good old friend that we are using for a couple of years, and that is ChatGPT. And ChatGPT, as we all know, is better than a crystal ball. Because crystal ball we could not have really used, we had to have an interpreter, and now if we understand the topic, we use ChatGPT, and if we understand the topic really well, we get very often frustrated, and we are learning where ChatGPT can help us and where it's really pointless. And if we are going into an area that we don't understand, then we are extremely happy with the results of ChatGPT because we cannot verify their validity. And I don't know who was behind coining the keyword of hallucination for tools of this kind, but after my experience for the past few weeks when I was preparing this presentation, I believe this is exactly the right term and the right verb to go along when describing the output of tools like ChatGPT. The other tool that I will be trying to sell you on a bit is a tool that we developed at Masaryk University, a tool called SecCerts that I also used for a part of my presentation. We have heard here and will be hearing more good arguments in favor of certification. And if we take a little bit broader scope than certification of cryptography or certification of security, we look at certification of IT products. We already have heard that what is behind is interoperability. We have heard of some aspects, definitely clear aspects of quality assurance. Of course, market trust is closely tied to that and is definitely to the industry probably worth having a separate box on this slide. Compliance, and last but not least, competitive edge for companies who can score the first certifications and come with certified products first in the market. However, there are also negative aspects. Cost. We have heard cost being mentioned today, and it's cost in terms of money, people, and resources. Many people could do more inventive, more creative things than bothering with certification. It's time-consuming. And it creates a non-trivial maintenance overhead. Dan mentioned in the intro here the issue of maintaining the infrastructure and the systems that we introduce to support us in our daily lives. But the same goes for certification. Once we introduce a certification scheme of whatever kind, we introduce the requirements maybe for products to go along this line, then they will have definitely limited validity. They will have to be recertified. The standards themselves, the benchmarks against which the measurement is done, will be developing as well. And both these will feed the need for recertification and added costs in this dimension. Let's not forget that, unfortunately, certification also sometimes inhibits innovation, or partly inhibits innovation. People go, look what the customers want, and when we get the market into a position that the customers want a certified product just to clear the tick box to be compliant with scheme X or Y, then the customers want a certified product. They are not asking for a special feature that only we can do. They want a certified product. If the market goes in certain aspects this way, it is definitely hindering innovation. And last but not least, fragmentation of the market. Standardization and certification, if done in different regions, different countries, differently, will fragment the market, will create additional costs. Let's not keep forgetting about these negative aspects of certification while we get today enthusiastic about certification. And I am enthusiastic about certification, but I want to keep these negative aspects on mind, and I would beg you to do the same. So let me entertain you first with my first ChatGPT dialogue that, if I remember correctly, I was waiting for somebody in the middle of Tartu, the beautiful city in South Estonia, and had a coffee and did not have any beer, and started playing with ChatGPT to spend my 20 minutes of waiting. So my first question was, give me some real-world examples of famous product certifications. And you can imagine, in IT, of course, Wi-Fi, you can imagine FCC in the US. You can be surprised that one of the security certification schemes comes already in the top 5 that ChatGPT fires on you, and that is common criteria. I was surprised, actually, to be honest. Then Underwriter Labs, and another security thing, PDI DSS compliance, payment systems. So according to ChatGPT, this crystal ball of this day, among the top 5 certifications in IT, 2 of them concern security. So I am a security professional and academician. Then I asked what were the worst failures of the products that were certified. Some people may remember the 1994 and the new Intel processor of that day and the fun that it brought us in the mid-90s. All of you will probably remember this one. And here we go with the first security one, Heartbleed. I believe that all of you will remember that one. And another one, the very famous in the US, not so famous in Europe, failure of a wide government effort to provide a secure platform for sharing and doing some operations with healthcare data. And the old textbook example of the Terac radiation machine that we have been learning on already in the 90s. So again, out of the top 5 failures, 2 of them are of serious concern to us here in the room. Well, then I was more curious about cryptography, because I was asked to speak more about cryptography than security. So, of course, number 1 was Heartbleed. Number 2 was Roca, probably well known here in Estonia. And number 3 was Snowden-related generator, allegedly co-sponsored in development by one of the famous US institutions with 3-letter acronym. Then I was driven away by the hallucinating machine of ChatGPT and went to thinking, okay, how was the world of crypto when I entered it, and how was the standardization then in the early 90s? Well, it was living with the big standard of DES and people in the academic community frowning about DES, complaining it's an algorithm from the 70s when a US government had a call, ran the competition and discussions only in the closed circles, tweaked some parameters for the better of the ecosystem, at least that's what we believe so far, and tweak other parameters for the good of the American government. Then, in the 90s, when I entered this beautiful world of cryptography, it was actually the effort, and here I'm speculating, I have to admit, of a US government-related folks trying to make sure that no better algorithm gets really standardized and the impact of DES remains in validity as long as possible. So this was the world of standardizing new cryptographic algorithms, at least to me, in the previous century. Still, from the previous century, we have this new algorithm of AES. We speak of AES as a new algorithm, maybe not rightly so. It's a quarter of a century already. Quarter of a century old algorithm. When the call came, there was some criteria for selecting this algorithm. At the very high level, the criteria went this way: security, cost, and characteristics of the algorithm and implementation. Those who followed the competition then, or read about it in detail, may remember that these criteria were twisted during the process. They were modified in the following way. Security was split into two parts. One was general security. Then the performance of the algorithm was more translated or more shifted towards the ease of the implementation in both software and hardware. Specific attention was given to the implementation attacks. This is the heritage of the 90s and Paul Kocher and other people inventing new things that were unknown up to then. And flexibility in decryption, keying, and other factors. These are not very different, but they are different. And many people then who believed in, or who were very rigid with respect to expecting fair competition, were actually pushing hard for the criteria not to be modified this way, although from the perspective of today, I believe that this is a modification in the right way. Recall the results of this competition. It was a US competition. Surprisingly enough for most of us in Europe, it was actually won by a non-US algorithm. Those who are old enough to remember that competition, this was a shock for the community actually. And it was an algorithm that out of the five finalists in the competition was not carrying the label high security, but the lower label adequate security. And algorithm, to be honest, that had very nice, very convincing performance advantages, both in software implementations as well as hardware implementations. There were more secure algorithms in the competition. Some of them were much better in hardware, or had a clear potential to be better in hardware. Some of them had potential to be much better in software. But this was a reasonable compromise with which we are living for 25 years, and so far, so good. Then I went back to ChatGPT, and here I got toasted. I spent several sessions under my different IDs and different logins with ChatGPT because I was not happy with the results that I was getting, because I was not asking about the archaeology of security and cryptography. I was asking about what's going on, what's the hot stuff on the boilerplate. And I was getting things that I selected here are the reasonable ones. I got about 2 to 3 times more of nonsense and blurb for the journalists. Then I left ChatGPT, and we have heard today about some schemes, and not all of them have been mentioned. So I want to mention here several schemes with which we already have been living, with which we are learning to live, and with which we will have to learn to live. And I don't want to comment too much on these schemes, while most of us in this room may be happy, because we'll have a lot of work to do. If I had a security company, there would be a really nice business in Europe for a few days. People who are on the other sides of the table may be not that happy. We keep hearing of the words of overregulation, costs, and many good arguments why maybe this plate is too excessive. Future will tell. I don't want to comment on this anymore, and let me focus on cryptography. One of the relevant things that comes from very recent past is the new update of FIPS 140. While we pay attention to version 3 now, and for very good reasons, we still should keep on our minds that until late next year, the validity of version 2 is still in place for some use cases. And attention to this US standard is, in my view, and my take on the European discussions, going a little bit down, and maybe rightly so. Maybe we do a mistake. Maybe this standard will be as important as it used to be in the past 20 years. We shall see. Before I get into the final parts of my discussion, let me guide you through the common criteria, important concepts that I will need for the last dozen minutes or so. And that is the target of evaluation, that is the stuff that we want to evaluate, protection profile, the, let's say, subset, typically specific subset of common criteria along which we want to drive the evaluation, and security target, the ultimate concept or aim, sometimes we can view it as a claim, what our product is actually achieving. And we know, do I have a pointer? Nope. We know, or if we don't know, I'm telling you, that the evaluation is not done in a way that a vendor throws a product on the table of the evaluator, but the product must be provided with a lot of accompanying effort and documentation, and together with the security target, that is the theoretical claim, this is what my product does. And the evaluator is doing the job of evaluating whether the product does this thing. Okay? So the security target is extremely important for us. It's important to me as well for the beers, of course. And where the security target can do it, I believe it should do it, goes along and stems from the protection profile. However, for the modern technologies, and we want to discuss here modern cryptographic methods, it may be tricky and sometimes, especially in the beginnings, not possible. Oh, sorry, I jumped back. Let me take the first case, homomorphic encryption. All cryptographers are enthusiastic about homomorphic encryption, I would say for a quarter of a century. Longer than AES, if I recall correctly, or about the same time. Homomorphic encryption, at the moment, is, if my information is correct, and here I went beyond ChatGPT, is not in any government-approved set of algorithms. And just last year, only two algorithms came out in the part 6 of this ISO standard that I'm quoting here. There are a few reasons for that, but we see in the industry a clear interest to start working with homomorphic constructions. We see first potential customers testing and playing with the thing. And we see also the first products that get certified. first product, to be honest. If I checked correctly, and I rechecked this week, we have one product that is certified. And the certification, I did not read every single line, but it left me puzzled, and I believe that when I will go through this slide, it will leave you puzzled as well. On one hand, it says that the target of evaluation, the product that is evaluated, the thing that the vendor is bringing, is a homomorphic encryption engine for database queries. My heart and my soul would want to say, wow, that's better than beer, isn't it? Well, then you read this. And I took the quotations, so sorry if I'm harming a soul of our vendor's interest here. It was not intentional. You were the only one having this product, and I went to analyze this document that is available. And that it basically says that it's evaluated as software application only. Maybe I should have underscored this. And the homomorphic encryption techniques, blah, 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 are left outside the scope of this evaluation. Okay, this is already interesting. What's behind? On one hand, it says the target of evaluation is the homomorphic encryption library version XYZ. So it is, the library is evaluated. On the other hand, it says specifically the excluded functionality is the homomorphic encryption process, including the algorithms, uses, and the security strength of the resultant ciphertext. If I'm paid as a consultant, am I recommending my client to use this? I don't know. Definitely not for security reasons, and definitely not as this being a competitive edge. And reading of these certification documents will leave you left puzzled. If you focus on the cookbook, it should go along, and the cookbook is generic application software protection profile. So protection profile along which you can evaluate security meters for monitoring potholes on Czech roads or anything else. So much for homomorphic encryption. And here we speak of a construction that is, for me, the first things really like quarter century. Not think of past 5 years. Then we have another interesting area, and that's multi-party computing. And multi-party computing, I will divide into two branches. One is with short or relatively short data, and that is for crypto key operations like signing. For that you will find quite few products, and supported by security targets. And you will see also situations that the security target is a little bit shy of the MPC aspect. It's done internally to secure the keys, and the conformance is claimed to cryptographic protection profiles that basically do not consider much of MPC aspects. And I can understand. There are so many protocols, and so many more are being developed and still evaluated. And we don't have any real standards along which we would robustly build the entire certification ecosystem. And then we have the other branch of multi-party computing, and that is working with data that is bigger than standard cryptographic keys. Typically here we have solutions that go for privacy-preserving data analysis. And here we come into even more tricky area, because we work with different aspects than the aspects of cryptographic key protection. Cryptographic key protection is a business that is very well known. It's understood clearly in lessons learned in a very hard way, where it fails, what gets screwed, what threats are there. For bigger data operations, for true multi-party computing, it's trickier, and developing the right thread model is unfinished business. I have not seen a paper that, except for just one particular case, one particular thing, really would show me a thread model that I would happily read, agree with, come back to that paper or white paper 1 week or 1 month later, and still agree with that thread model after thinking about it. And on top of the 2 slowdown factors that I see in that area, it's also the performance overhead that are tricky and that play against the fast deployment in the industry. So to conclude my presentation and my discussion, I come back to my crystal ball of 21st century. And this was really not pleasant. I had a discussion with ChatGPT after putting through results of previous discussions. And I asked about the vision of certification of new products and standardization. I got this answer, which is okay. I think that nobody here in the room will disagree with that. I got this answer that will not make me unhappy, but will not help me probably much. And I sort of felt like this. If somebody gets me this keyboard, it's a keyboard that's useful for certain situations, but not for general work with a computer. So here the crystal ball actually, or work with ChatGPT, led me to the thinking that as a crystal ball of the sense of looking into the future, it's still a rather hopeless tool. And when considering the aspects of certifying new cryptography, I thought of non-cryptographic takeaways that I'm putting forward. And one is really going back to the basics and figuring out why exactly do I want to certify my product. Do I do it to make one particular customer happy? And if so, it's perfectly right decision, but I should stick with this, and I should keep this reasoning, this decision on my mind, even in 1 year or 2 years, when the situation maybe changes, and maybe then my position will change a little bit, and I will want to go ahead and look into other aspects. Of course, we have a trouble with quickly developing ecosystem, yet we should try to map the ecosystem, and we must make sure that we map it well. And last but not least, the world is not perfect, we are not perfect, we are making mistakes. It's definitely worth doing things in order to avoid the mistakes. However, we should not really fear them and inhibit them from us doing what we want to do. With that, I want to thank you very much for your attention. And to add a little bit of my games with the crystal ball, the last image on this slide comes actually from ChatGPT. I got ChatGPT actually repeatedly stuck on regenerating a different image when asking for the requirements. I leave it for the coffee break to discuss where I got it stuck. And with this, I want to announce, beyond the chess project that is ongoing project on really interesting collaboration in different 6 areas in cybersecurity, a project that is called CCAT. That's what the logo shows, the CCAT. Project that we start with the consortium here from Estonia involving 2 partners, University of Tartu and Cybernetica, where we will be evaluating 6 very specific tools, some of them concerning cryptography, namely TLS, cryptographic certifications, certs, cryptographic evaluations and certifications for special purpose hardware like smart cards or TPMs, scrutiny, and ALVI, a tool for embedded software security, will be evaluating these, and we will be very likely, in one way or another, reaching out to you if you work in an institution that would want to put their security a little bit forward, try and help us improving these tools, and in favor getting our assistance in helping to verify your TLS deployment, your smart card deployment, or your considerations in the world of security standards. Many thanks for your attention.
Thank you, Vácek. Now, as the time is up, but fortunately there's a 20-minute coffee break. So you can find both Vácek and Eric and everyone else you want to talk to for 20 minutes, but then come back because we'll have 2 more exciting talks.
Please.
Thank you. That was awesome. We are starting with the second block. There's 2 talks again. First, we'll again tell you about changes in certification policy, but a little bit more. I admit that I wrote the title and Miguel was a kind gentleman and kept it. I wrote some, tried to write catchy titles so that people would come to the event. So this one is my fault. I'm not sure Miguel would have used it, but he did in the end, so I'm very thankful for that. So Miguel knows, again, more about common criteria than I likely ever could. So please.
Thank you. Does this work? Okay. First of all, thanks a lot for inviting me here. I'm here in this Taylor Swift mode with the speaker thing, but I will not dance or sing. My name is Miguel Bañon. I'm very happy. I have the pleasure to convene a number of standardization working groups responsible for those standards that are to blame for many things that have been discussed here. The first one is ISO IEC/JTC1 ST27 Working Group 3, responsible for the common criteria, also for the 19790, the security requirements for cryptographic modules. In Sensenelec, at European level, I'm also responsible for the same type of working group for evaluation methodologies, Working Group 3, and lately for the new working group dealing with cryptography, which is something new in Europe. But as Dan has introduced, he invited me to talk about Bluetooth toothbrushes. And I said yes, because I didn't know it was such a huge thing. And it is. So let me solve first the challenge from Dan, and let me talk to you about the Bluetooth toothbrushes. And hopefully at the end of the presentation, have some free time to speak about my safe zone, about the standards, common criteria, all those things. But I'm, of course, happy to discuss at the breaks and at lunch of whichever topic we may find interesting. The short answer is yes, toothbrushes need to go through some type of conformity assessment dealing with cybersecurity. And it really will depend on the functionality of the toothbrush. I will go through many concepts. I'm afraid you will be familiar with most of them, but it's important to refresh these things. For your information, my past background for 20 or 30 years, I don't remember how long I've been working, I was born in this niche of Ministry of Defense classified assurance project, certification schemes, voluntary but mandatory because of procurement. And when we talk about certification, we have the same idea in mind. But that's the past. That's a small niche. That has no relevance in our new European market. The toothbrushes are the important thing from the legislation and from the standards point of view. It's not about cybersecurity, it's about any product meeting the requirements that legislation requires them to meet for them to be sold in Europe. Safety, health, whatever. And we have something called the new legislative framework, which is a very old one, still named new one, which the conditions and the methods to provide proof of conformity for those legal requirements And once your product, you are able to show that you comply with them, then you can sell them. And in this big framework, which is a huge thing, it will take you some time to read it and fully understand it, there are very important elements which has to do, who provides the assurance, who provides the evidence, who provides the test reports. And in our legal system, European legal system, there is a big confidence in first-party testing. First party is the test developed by the same developer. I will produce the toothbrush, and I will do the test myself. And that is good enough for me to sell that in Europe. In conformity assessment, we have the concept of first party, second party, third party. Second party is when, let me go. So first party is when the developer does the test themselves, okay? And second party is when the customer does it. A big supermarket chain, they will buy toothbrushes, but they are not sure they don't have. So the supermarket chain will test for themselves. That's second party. And third-party testing is what we are talking here about certification. Okay, it's not going to be the developer, the manufacturer, it's going to be somebody else. And that somebody else, also requested by European law, will have to be somebody who has accreditation. That means that they comply with some standards, and they have a legal entity, and they are notified to the European Commission, hey, I am able to tell you whether the toothbrush is secure or not. I am able to tell you this or this or that. So for high-risk products, for products where we are risking our lives or we're risking something important, the EU legislation requires third-party testing. But for most of the products, first-party testing is good to go, okay? And that's good because that solves the bottleneck that going to a third party creates. And whether the product has to go to certification third party or first party has to do with the intended use. A toothbrush is to brush my tooth. If it's a connected, a smart toothbrush, it's still for that. But maybe I can use the interface to trigger from my toothbrush a nuclear bomb. That is outside of the scope of the intended use. Okay, so even if it becomes a critical element in pushing the button for a nuclear bomb, it's not intended to be like that. Okay. So let me skip about these things. And how do you make sure that your toothbrush complies with the regulation? When the European Commission, those people living in Brussels with no sunny days like this, they think about lovely new regulations everybody needs to comply. They go up to the abstraction level. They go up there. Products shall be secure. You humankind will behave. So kind of the 10 commands of. And okay, how do you check that? You need some technical details. How is a product assumed to be secure? How it's not on the law. So we have this mechanism in Europe that for all these regulations that at the end of the day require some technical interpretation, that will be solved by something called a harmonized standard. So a harmonized standard is the projection of the legal requirements into a state of the art. Okay, how is a secure toothbrush intended to be? Well, it has I don't know, a button for start, stop, pair on Bluetooth, and do this or this or that. And the requirements should be in the harmonized standard, so clear that the developer can take the standard, okay, check, test number 1, this. So it's an interpretation of the legal requirements into a state of the art. But not everything can be assumed as a harmonized standard. First of all, they have to be developed by serious guys, and that could be one of the standards development organizations in Europe. And second, it has to be requested by the European Commission, hey, guys, we have developed a new small legislation, it's called Cyber Resilience Act, please develop standards for all the products in the world. So that becomes a standardization request to Sensenelec, ETSI, and a contract, okay? And once they provide and finish those standards, they are published in the official commission. And then if you are a toothbrush producer, manufacturer, you find there which standard you have to meet to have something called presumption of conformity. If I do the test, if my toothbrush passes the test, I have presumption of conformity. It is assumed that my product meets the requirements of the law. I can put the CE mark in and put it on the market. Okay, this is the framework, and it's not for cybersecurity, it's for everything. What is new here is that those guys in Brussels with no sunny days have decided that cybersecurity should also be part of this framework. You cannot put a product in the European market anymore without some considerations for cybersecurity. And that's good in principle, okay? Nice ideas are good in principle until you see how they are going to be implemented and when problems come, okay? And we have one previous experiment before we talk about the big thing, which is called the Radio Equipment Directive. This is a relatively old legislation, about 10 years ago. This is about requirements for anything that has a radio interface. And the requirements there are mostly dealing with electromagnetic compatibility, have to do with safety. If you have your pocket, your mobile phone close to your head, it will not fry your brains. So it has a number of requirements, and it has associated harmonized standards. So it's very trivial to check compliance with this. You put the phone, you put it on top speed, top power, you measure the signal, and you see that it doesn't pass the limit. Okay, so it's a very straightforward thing for products that emit radio emanations to be safe and to be nice to be used in Europe. But in 2021, there were 3 articles that could be read that were not into force until then, and could be read with some point of view from cybersecurity. And then the Commission said, hey, let's do an experiment here. Let's push these requirements, and let's interpret them, and let's make them officially a requirement, and let's see what happens with all this. So these are the articles, Article 3.3, E, and F. And the first one has to do with protection of personal data and privacy. So in principle, if the device has personal data, it shouldn't put them at risk. The device itself shouldn't be used for fraud, economic fraud. They should, if you have, I have on my phone the credit card, I can pay with near-field communication. So if my phone is able to talk through radio and I have my credit card there, nobody should be able to steal money from me, okay? And of course, the last one is, okay, if my phone is connected to this 5G thing or whatever, it cannot be used to harm the radio, the network, okay? So there are 3 general, very common sense requirements that until now, were not required for products to meet, but now they have. So the Commission said, okay, from now on, any product with a radio interface has to meet these 3 requirements. And this is nice. How do you check compliance with the first? I have no clue. With the second, neither. The third. Then we need harmonized standards. And these harmonized standards will tell you what are the security requirements and how to check for that. So first of all, is the toothbrush subject to these cybersecurity requirements? Yeah, it has a Bluetooth interface, it has radio, so in principle it does, okay? So, but these regulations don't have a list of specific products. They talk about categories, and of course, it has to do with intended use. So, for the requirements to be applicable, the toothbrush itself has to have some functionality that is related to that. So what if my toothbrush, for example, registers my habits? When do I or I don't clean my teeth? Or the location? Or my strength? Or something which could be medically interpreted, okay? What if my toothbrush has an internal refill of the toothpaste, which I can pay online, and okay? So I have an account, I can pay for refill. So it has some data could be used to get money from myself. And what if my toothbrush could be connected via Wi-Fi and used as a proxy to attack my network at home? So you see, it depends on the functionality of the toothbrush. It may or may not fall into these requirements. And that's up to the developer, or the importer or the producer to decide whether these requirements comply. Okay. So some time ago, the Commission asked Sensenelec, JTC 13, to develop harmonized standards for these three things. And surprisingly, they did. This is Working Group 8, which did a fantastic job. And they have published European Norm 18031. And these standards are the first standards we have in the normative framework in Europe, which are harmonized standards dealing with cybersecurity. We never had something like this, okay? Because the rest of the harmonized standards have to do with electronic compatibility or simple checks, but these ones are the first one for cybersecurity. It's one standard per article, and in these standards, you will find the requirements that the products need to implement and the testing methods. So the developer can do first-party testing. Or the developer, if they are too busy, they can hire a lab, and the lab will do the testing for them, but it is a first-party activity. And they have been adopted by the Commission, they have been published on the official journal, and if your product complies with them, you can have presumption of conformity, and you can sell the toothbrush in Europe. And there we go. There are a few mistakes on the standards, and the citation excludes some minor things, but they will be fixed. But these standards are, it's like a small step for the standardization community, but a big step for the market, because these are the first examples we have here. If you compare these standards to the common criteria, to the other things you have been discussing, you would be surprised because they lack specificity, they are very generic, and the testing methods, well, for example, crypto, they say if you use crypto mechanisms, the product should use a state-of-the-art crypto, which is a nice thing. So my question as a tester, what is a state-of-the-art crypto? No clue, okay? So there are some gaps there. But I think it's very important that we take this into consideration. This is a badly drawn attempt to put here on a graphic the law of diminishing returns, which applies to mostly everything, but especially to cybersecurity, assurance. Okay, if I do some investment, I want to improve my product, and I do some investment there, if my initial situation is zero, with a small investment, I can improve a lot the security of my product. For example, if I have an application, I don't have authentication, I don't have accounting, I don't have anything, it's rubbish. Going from rubbish to something useful doesn't cost you too much. However, once I go to some level of maturity, to improve that will take me a lot of money and a lot of effort. So if I spend 10, I probably, from 0 to 10, I will get an application or a service which is 10 times better. If I spend 20 or 100, I will not get 100 times better. So this is the law of diminishing returns. And when we apply this to cybersecurity, this is a truth we cannot avoid. The most return of the investment is in the low-level stuff. If you look at the products we have today in the market, they are at the origin of the coordinates, to say it elegantly. So a small requirement will improve a lot the cybersecurity of the products in the market. Just making the developer to consider, to define the assets, okay, your toothbrush, what is protecting? Today they don't know. They will have to make an analysis. They will have to decide how to protect those things. And then they will have to decide how to test those things. So even if the standards are very generic, even if they require very simple security measures for the products, my view is that they will have a very big impact on those radio-connected devices. Of course, those familiar with the third-party conformity assessment scenarios, with the common criteria, with the FIPS, all those things, when they look at these standards, they look with some condescent, but they are already living in the high assurance area, where a lot of money is spent and products already have a lot of maturity and a lot of security level or assurance. Okay. So this was a test or a trial, because the big thing is coming now, which is the Cyber Resilience Act, and Eric already mentioned that. And this is, they're going to, I asked before producing the slides whether these would be broadcasted or something to see how much I could. And I'm told this will be recorded and later able to reproduce. So I will be very limited on my personal views here. But this is big things coming, okay? And it's already published. It's already approved. But it's only that obligations will not be fully into requirement until December 27, okay? So vendors have until 27, the end of 27, to make sure that the products comply with these requirements, which is good. And this will be now not only applicable to products with radio interfaces, this will be applicable to anything with digital elements inside, any microprocessor, I mean, every product. And not only when they are developed or designed, this will apply to the full life cycle of the products. Okay, so it's a very, very big thing. So it's already published, you can read there, and the requirements that this regulation is asking the products to meet are very common sense. If you read that, you will have no objection. The product should be able to be updated when a new vulnerability is discovered. Why not? And you can do if you can try to remove requirements from there, say, okay, no. Don't ask them to be upgradable. And then what? So most of the requirements there are common sense, no questions about that, okay? But of course, the regulation is very high level, so we can, again, to the same issue. How do we make sure that the products comply with those? Then we come again to the harmonized standards. So there is ongoing development, and this is going to be quite an adventure. The European Commission has requested the European standardization development bodies to develop harmonized standards for all these. And the problem is that this regulation applies to anything on the market that has a digital element. So we need standards for everything, which is quite a challenge. The standardization request requires 44 standards, but Sensenelec and ETSI have the freedom to reply back with a different design. But at the end of the day, they are asking for two things: horizontal standards that will take into account the life cycle parts of the product, vulnerability management, security by design, blah, blah, blah. And every vendor, every manufacturer, everybody who produces any device, software, or whatever to be put on the market will have to follow these requirements affecting their engineering processes. One of the things of cybersecurity, you cannot talk about cybersecurity if you don't have some level of maturity of your engineering. Cybersecurity is another non-functional quality of a product. So if you want to control the qualities of your product, you need to have a good engineering process. And the engineering process for cybersecurity is not different from any other quality factor. So gone are the days of doing something, I don't know what's inside, and put it on the market. Those days are gone. They have to take into account a lot of considerations that modify the development in the economic model, engineering process, everything. And then you are able to produce a product that may comply with all the regulations from the European company. So then these are the horizontal standards, and we have vertical standards. Why? Because a CPU is different from a firewall. A firewall is different from my toothbrush. And we need vertical standards for all those things. Of course, as I said, it's about the intended use. My toothbrush is not going to be normally used to fire a bomb, a nuclear bomb. But there are devices to fire a nuclear bomb. And there are devices to control this or that or whatever. So the CRA has this concept of risk, and the requirements change according to the risk of the product. So for most products, these horizontal and vertical standards will allow self-conformity, will allow first-party testing. But for some other products, that is not good enough. I don't trust so much the developer. The developer may be, coming back to the trust elements, so for some critical products, I want to have third-party testing. Okay? So the CRA has a list of product types where the legislation considers first party is not good enough. They have to go to third party. Okay? And now we are talking. Now we are back to certification. Because for those critical products, the third-party testing will have to be done either through one of the certification schemes that ENISA is developing, okay? Or they can go to a normal third-party conformity assessment, because all this is about the usual framework for products in the market, NLF, newly, so there is nothing new here. But the list of critical products, they will have to get third-party evaluation and certification. For self-assessment, we have harmonized standards. What standards do we have for third-party? Okay, and now I'm in my safe zone. For product security, for product evaluation, the classic standard that we have is on the top left, the common criteria. Sorry for the diagram. The common criteria is well known, has been there for 20, 30 years. We are completing a new revision. There will be a version 2025. And it's always evolving, adapting to the needs, and happy and more popular. However, at European level, we have developed 2 additional methods of third-party testing. The first one is called fixed-time evaluation methodology for ICT products. It's a different way to do testing. This comes from the trials from some European schemes having on place something quicker than common criteria. And we also have something called CESIP for composition. So we have found some European specific needs, and we have some standards that try to make the process cheaper and more efficient. That's for general products on the left-hand side. On the right-hand side, crypto. For testing crypto modules, we have ISO 19790, the old FIPS. Now the new FIPS refers to this standard. We published version 2025 2 months ago. And on the European level, we have yet not published any European standard. The working group is new, and we're still going slowly, and so on. So let's meet again on December 2027 and see what happened with the CRA. That will be nice to discuss. I'll stop here.
So, thank you very much, Miguel. Here's a tiny...
Oh,
thank you very much. So let's now think of how a country the size of Estonia can reasonably try to do all of that. So the study of that has been going on for about 1.5 years. And to present some of the first findings, we have Kristjan Krips here. And yes, that'll be the sort of a reality check for smaller European nations.
Hello, I'm Kristjan Krips, security engineer at Cybernetica. And I'm going to speak about the challenges of building conformity assessment ecosystem in a small country like Estonia. And my talk is based on the results of a state-funded study done in 2024, which aimed to map the capabilities that we have in Estonia in that field and the potential to develop this ecosystem so that it could be decided whether and how such an ecosystem could be built in Estonia. When thinking about the need for such an ecosystem, then it's quite clear that we need to see whether the cryptographic products are complying with the requirements, whether they do what they are intended to do. But certification is something specific, like it was mentioned in the previous talks. And it used to be only required in very specific areas and under very specific regulations. And now, as we saw from the previous talks, as EU is introducing new regulations, the need or demand for certification will increase. And there will be also a demand for evaluations. And maybe this means that there is also a need to establish evaluation labs. And maybe this could also be done in a country like Estonia. So this is one side of the view for this issue. The other side is that the state also needs to assess how cryptography is implemented in governmental systems. And more specifically, Estonian National Communication Security Authority needs to decide whether some cryptographic products can be approved for use. So these are the two main aspects when considering the need to build this ecosystem. When looking at this, the goal of building the ecosystem, then we quite soon see that there are quite many challenges and quite many complexities. And I thought that maybe this image would illustrate that. So the image shows normative references among ISO standards that describe conformity assessment. And it's a simplified image, which only lists some of these ISO standards, and it has a reduced number of arrows, otherwise it wouldn't be readable. So it displays the same standards that were just mentioned, the standards that define common criteria, the standards that define FIPS 143, and other conformity assessment standards which describe how to set up a lab, how to test for randomness, and so on and so on. And now, where to get the people that have this knowledge? If you don't have the ecosystem in Estonia, then most likely we don't also have the people who have read these standards and who have experience with working with these standards. So what we did, we mapped the capabilities that we have, the human resources, the number of cryptographers in Estonia, the number of companies working in the field of cryptography, the requirements from the state institutions, and also the viewpoints of universities. Universities are these organizations which lay the foundation for the industry. If you don't have universities teaching cryptography, if they don't do research in that field, then we don't get the people who would set up this ecosystem. So we started by checking what we have in Estonia. And in general, you would have to have these institutions which are listed on this slide. So to do a conformity assessment, for sure, you would need an evaluation lab. Evaluation body, ITEF, or yeah, an organization that actually does the evaluation, the security testing for cryptographic software or for a cryptographic module. And the other conformity assessment body that would be needed is a certification body that basically takes the report issued by the lab and then checks the report, and if it's fine, then issues the certificate saying that the product complies with the requirements of the certification scheme. We have neither in Estonia, and we would need to have accredited lab and an accredited certification body. Then we also would have to have a national accreditation body. That one we have in Estonia. It's fulfilled by the Estonian Accreditation Center, but it doesn't have the capability to work in the field of cryptography. We also have our NCCA, or National Cybersecurity Certification Authority, which is designated by law, and this role is fulfilled by the Consumer Protection and Technical Regulatory Authority, but this organization also doesn't actually have the cryptographic capability, although they are assigned this role by the legislation. And then what we have the approval authority, Estonian National Communication Security Authority, who has to approve certain cryptographic products. When looking at the human resources, then we figured out that there are fewer than 30 cryptographers in Estonia who have published scientific papers about cryptography, and less than 10 of them work with post-quantum cryptography. And many of them work in the private sector. And cryptography is mainly taught in the universities of in University of Tartu and then Tallinn University of Technology. To get an overview of the state of cryptography in Estonia, we did actually about 30 interviews with different stakeholders, with companies working in this field, with the state institutions, and also with universities. And now I'll just give a brief summary of the findings that we got. In general, everyone said that we have too few cryptographers and security engineers in Estonia, and they are already working either in universities or in private companies. So it is quite difficult to build new capabilities as we would just have to somehow find new cryptographers, and they are already occupied with the things that they are currently doing. We also cannot directly employ students because they don't have the necessary experience, and the experience comes with the practice. So they have to work usually in the private sector. They have to implement something, they maybe have to break something, and once they get the experience, they could maybe be recruited to work in this conformity assessment ecosystem. But to do that, we also would have to have many companies working in the field of cryptography, which we actually do not have. And then what the solution is, some of the companies in Estonia have started to recruit cryptographers from abroad. Because if you want to expand the business, then, well, you need to get the people, and there are two options. Either you recruit from abroad, or you train new cryptographers, and that we are also doing. The universities are increasing the number of students who major in cryptography, but that's a slow process, and it takes years to get new experienced people. Now, when we spoke with researchers and cryptographers at two main universities in Estonia, then both of them gave similar answers, that they have two main problems when teaching cryptography. And the first problem stems from the educational system, that the educational system doesn't provide the universities with students that have sufficient skills in math. And you really need the math skills to study cryptography and to do research in cryptography. So if you don't have that, then you can't go and work in this field. And that's a real problem which has to be faced. And then during the study, we also point out some directions that the state could go to solve these issues. And the second aspect that the universities brought out is that as there are quite few students that enroll in the introductory crypto courses, then they don't have a sufficient amount of students who take the more advanced courses, because if you only take the intro courses, then, well, you won't be the researcher. Maybe you can be an engineer, but if you want to do research or if you want to do more complex stuff, then you have to also take the more advanced crypto courses. And how to solve that? You have to somehow motivate the students to major in cryptography, to take more crypto courses. And then there also has to be a demand from the labor market. And when we interviewed the companies, then many of them said that what they need from the universities is that the universities should offer more courses that give practical experience to the students about applied cryptography, engineering. So these things could be taken into account. Now, about the opinions of the interviewees about the conformity assessment and whether this should be established in Estonia or not. In general, quite many of the interviewees were skeptical about this idea, as we just don't have the people. And then the other problem is that as we don't have too many companies working in the field of cryptography and building crypto modules, then where would we get the market demand for such services? So to build conformity assessment bodies, you need customers who want their products to be evaluated, certified, and if you don't have the local demand, then, well, we would have to export these services and compete on the global market. And what else the interviewers said was that they only consider certification of their products if it is mandated by law or if there is a direct demand by the customers. Certification is so expensive and time-consuming that basically no one is willing to do that if there is no direct necessity. And then when interviewing state institutions, then it was also mentioned that some institutions need to assess the security and conformity of products processing classified information. And then when building that capability, then it is reasonable to build a joint capability so that evaluation methodology would cover both civil and defense sectors. Of the companies that we interviewed, only 3 companies had practical experience with certification, but some others had considered doing common criteria certification, but hadn't moved forward due to the cost or complexity of the process. The companies and the people who had experience with common criteria told that the first thing that the company should do when considering certification is to define a security target. The same thing that was mentioned earlier in the morning. So you first have to define the security target, write down what you want to achieve, what are the limitations, what are the assumptions, and then once you have defined that, you can move forward. And then you have to design your product in a way that it meets the security target and that it is certifiable, which means that you have to write the proper documentation. Otherwise, certification or common criteria certification is just not possible. And some companies also said that if you do it in the wrong order, that you first build the product and then try to certify it later on, then you will just spend much more money and you will need 1 additional year at least to get the product certified, if it is even possible. And yeah, it was also mentioned during the interviews that if your product uses modern cryptography, then it is quite challenging to certify the product, well, for the reasons that were mentioned earlier. There are just no suitable protection profiles available for modern cryptography. Now, as probably the evaluation lab would be one of the most important components of the conformity assessment ecosystem, we did a small cost-benefit analysis for establishing such an institution. And the main cost is for setting up the lab, acquiring hardware, for testing equipment, crypto modules, and then also setting up the facilities. And the operational costs are mostly tied to workforce. So you have to employ cryptographers, security engineers, quality assurance specialists, and that's quite expensive. And when considering the income, well, as we don't have local demand, then we would have to export the services. And just some numbers for simple common criteria evaluations. Well, the simplest ones may cost tens of thousands of euros, and for example, EAL level 4 evaluation can cost hundreds of thousands of euros for just evaluation alone. And there are extra costs for development and certification and so on. And the main risks for establishing an evaluation lab is that there is not enough qualified workforce, and there is not enough demand, local demand for these services. And if there is not enough demand for the services, then the question is that can the evaluation lab maintain the qualification of the specialists that it employs. So if the specialists get bored, and then we also got one example of such a case in one European country by one of the interviews, then they just change jobs and they quit. And if such a specialist quits in a small country like Estonia, then how do you get a replacement? You have to start from scratch by training the specialists, and that's a non-trivial thing to do. We thought, what are the ways forward? And we proposed 3 main approaches for developing conformity assessment capability in Estonia. And the first approach is to build a full conformity assessment ecosystem. So an evaluation lab, certification body, which both have to be accredited. For an evaluation lab to get accredited, it first has to show that it can do its work. So probably there have to be some pro bono projects at first. And then also to get experience with hardware evaluation, you would need some customers that provide their crypto modules for evaluation. So that would be probably a challenge. And what else we would need? We would need to acquire cryptographic competence for the national accreditation body and also for our NCCA. And in addition, we would need to create an evaluation methodology for Estonia, and it might also be needed to revise the legislation. Now, the second approach is somewhat more limited. Only the evaluation lab would be established, and the certification and accreditation services would be imported from other EU countries. And our NCCA would acquire the relevant cryptographic competence. And also the methodology for evaluation would be developed, and maybe also legislation would need to be adopted. And the third approach would be to create an informal evaluation methodology, an efficient methodology which would at first focus on software only, and also include guidelines for developers and leave hardware evaluation out of scope. And in this case, as we would not have an evaluation lab, so this would have to be procured from other EU states or from universities or from private companies. Where's the last slide? There should be one last slide. Oh, here. And conclusion is that It is probably not feasible to build the full conformity assessment ecosystem in Estonia, just due to our size and due to the existing cryptographic ecosystem that we have. But the second approach to build a partial conformity assessment ecosystem or the non-formal evaluation methodology could be doable. If the second approach would be chosen, then what we would need is the market demand. So we would need the industry to procure these services. Otherwise, the lab would not be economically sustainable. And if this methodology is developed, then it should be a unified methodology that covers both the products that process unclassified and classified information, because it's just inefficient to build two different methodologies. And what I would like to point out in the end is that all of this can only be done if we have a strong educational system. So if we don't have the educational system, if our universities don't have the capability to train more cryptographers, then well, it's not sustainable, and the ecosystem would not be possible. So, thank you, and questions?
Thank you, Kristjan, for that talk. And in the first row, Sas has a question.
Do you have any estimation about the size of local demand? How many certifications per year?
Let's say maybe one certification in a few years. Mm-hmm. So there is not much demand in practice. We have 3 companies who have done this over the years. So the demand is quite small.
Luís?
Thank you for the presentation. You mentioned challenges in the educational system, namely lack of motivation. Are there concrete ideas of activities or incentives to build motivation for students, like youngsters?
Yes, of course. So there are different funding programs to attract students into majoring in cryptography, but it's difficult because everyone wants to study AI. And machine learning, and it used to be blockchain, but yeah, now it's AI. So there are programs, but it's difficult to attract the students.
I will have some hope in my closing words. Please, in the front row, gentlemen.
If we take limited human resource as a norm for a small country, so does AI replace in cryptography specialists to some extent, or just can support those who exist already?
I don't think that at the moment AI can resolve this problem. Maybe it can review some documents, but it can only assist. It cannot replace the cryptographer.
You heard Václav's talk in the morning. One more question. Petr.
Thank you very much for the talk. You mentioned the small countries. Do you think small countries can join forces? You mentioned let's say, outsourcing or taking the evolution lab from other country, but we don't have it either. So can we just create a collaborative one?
That's a good idea to collaborate in this field, because, well, we have to find the solution, and that's one possibility. Yes.
Yeah, there was one more. Someone raised a hand. No? 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 No. Awesome. Working together with Czechia. Great idea. Thank you very much. I know we ended the first half of the day in a somewhat gloomy outlook. So now we're going to lunch. Then we'll get your blood sugar up. And then we'll have 2 talks about constructive tools and how we can go forward from here. And then take the collaborative idea up again after that. So now there's 45 minutes for lunch. Let's thank Kristjan again. So, welcome back. Here we go again. The first part of the day was to tell you what the words are, what the words mean, what the urgency is. You saw where policy and regulation are going. So, and in the end, you saw how it can be a bit of a challenge for smaller nations to stand up to all of this. However, as somebody already asked, can you use AI to do a cryptographer's job? So you may not be able to use AI to do a cryptographer's job, but you can try to use formal methods and other kinds of tools. So this block right now will be a bit about tools. And to get started, I am very happy to introduce Andreas, who will tell us about formal methods.
Thanks for having me. So, this title wasn't chosen by me, it was given to me. So, I will work along this title, and a spoiler, if you didn't read it, formal methods, fun for academics, or realistic tools for industry and governments. I would say it's both. I should say I am biased. So I am an academic mostly. I have a co-affiliation in industry, but my background is in what people call provable security. So I build cryptographic schemes and give handwritten security proofs that they are secure. And I started using these tools to actually verify that my statements are correct. So I specifically use a specific tool called EasyCrypt, and I'm part of the Formosa crypto project, which I might briefly introduce in the end if I have time left. And I have a co-affiliation in industry, as I said, with Sandbox IQ, and there I actually rather led a project together with a company called Kristjan, who developed a tool called Hex, and where we use this to actually verify a cryptographic API. And I will briefly come back to this later. Okay, so let's first look at why I think this is actually a realistic tool for industry and governments. This whole thing, as we heard in the morning, goes back to how do we build trust in cryptography, right? If people use cryptography, they have to be convinced that the stuff is actually secure. We've heard like Europe wants to use hybrids for post-quantum crypto. There are good reasons for this. But this is all about and how far did we already establish trust, right? And of course, if you're a NIST, then you just run a competition and you get enough attention on your schemes. And actually, if you do this, and for example, for cryptographic schemes, often you require that they actually come with a proof of security, then people will actually check these proofs, and over time, they will actually find stuff. So I'm the lead submitter of Sphinx Plus. And in 2020, I got an email from my now almost finished PhD student, Miguel. This was kind of his application for the PhD position, saying like, dude, you have an issue in your proof. And this was really, really deep in the proof. This actually came from a paper from 2016, I think. And an argument in there, and nobody saw this. This actually concerns XMSS, which at this point was already standardized. No one found it, because no one read these proofs in sufficient detail. And of course, I'm not the only one making mistakes. This is a different work where we looked at dilithium, and this was published 2 years ago. So we actually found this after dilithium was selected. And there we found that there's a subtle issue in the proof that not only concerns dilithium, but all lattice-based schemes that actually kind of follow the same proof idea. Luckily, in both of these cases, we managed to fix these so the schemes are safe, the proofs are recovered. But this is stuff that people didn't see, right? So what if you're not NIST? Well, let's take an example. If you look at the history of SSL/TLS, these are only the attacks I'm teaching in my applied cryptography course. Right? I've got slides from colleagues which have just pages full of red arrows with attacks from here and there. So these things actually turn out quite bad if you're not careful. Another example that I'm very proud some former students of us found out is the Tetra is the radio security algorithm used by European security institutions, like civil security institutions like the police and so on. And it turns out this was an ETSI closed standard, and this thing was utterly broken. So I think the slides will hopefully go online later, then you can use the links. Clicking on the screen doesn't work. And many of you might know OCB2, which actually became an ISO standard in 2009, and I don't remember exactly, but I think 2018, 2017, something like this, people observed like, hey, there's a flaw in the proof. And in this case, we were not as lucky as for the cases of Sphinx and dilithium. It turned out that this flaw could actually be worked out to a full attack, and OCB2 is entirely broken, like with no recovery. So you can actually fully break the security of the scheme in practice. And the mean thing is, so for these cases, like while for the NIST cases, the attacks were actually found during the competition, in these cases, the attacks were found during deployment, right? So the question is, how do we actually avoid this? Or where does this issue come from? We had this in the first, in the introduction by Dan. Yeah, in cryptography, you publish this paper, right? And then you write a proof, and people are reviewing this. I'm not sure if any of you ever looked at these papers, or papers that write a security proof for cryptographic protocols. They start with a description of what it means to be secure, which already fills several pages. They are extremely hard to parse, at least for me. Maybe other people have an easier life. And it's so hard that it's even really tricky to understand if they express a meaningful statement. And then you have, like for TLS 1.3, this is about 36 pages, model and proof together, like full A4 with hardly any margins. An example that we looked at was WireGuard, because we made a post-quantum version of it. This had a just 16 pages proof, where they built on other results. So this was really just a proof for the core protocol, assuming stuff like pseudo-random functions and hash functions secure and so on. And because they aimed for a stronger security notion, this ended up with 16 pages, and obviously they made some small mistakes, which we found corrected, and then actually we noticed that we also had issues in our proof later on. So this is really tough. And if you look, Signal was another example I picked up. So the first paper, I think, that analyzed the double ratchet, like this construction behind Signal, which makes sure that even if your keys get compromised, they actually are somewhat self-healing, right? So you gain security again if the attacker isn't consistently running an active attack. That thing has like 56 pages for proof and model, and assuming a lot of pre-knowledge already. So this is extremely hard to verify and to get right. And even if you manage to verify the proofs, there's of course more. So for example, these proofs build on what we have here on the left side, these algorithmic descriptions, right? So this is like how Kyber was published in the actual paper. But if you look at what the standard says, then you have the thing on the right side. And this thing on the right side actually depends on a lot of further functions which are specified at other points of the standard. Right? And if I prove anything about the left side, this only transfers to the right side if I can argue that this is actually a secure instantiation of what I wrote on the left side. Right? So this is stuff that we actually have to check. And then the stuff also has to get implemented. And also there you can make a lot of mistakes, right? So you had this example of Sony implementing ECDSA, and they implemented random number generation by returning 4, and I'm sure they sampled the 4 initially in a very random way. But fixing it, well, this is, of course, something where cryptographers say, like, come on, guys, how could you? But there are other ways how you can actually deviate from the actual standard and implement something that's slightly different, and especially if this is in some edge cases, like manual inspection, how this is nowadays done. If you do security certification, I think chances to catch this are extremely low, right? And then we have this whole business of side channel attacks, like if you don't implement your code in a constant time fashion. So if you have behavior that depends on secret inputs, you can learn this remotely. And it was demonstrated you can actually even do this over a network, right? So you can filter out the noise if you just get enough interactions, and then you can actually learn secrets remotely just by looking at how quickly the other side responds. And this is something we've also seen in the NIST competition. This was actually found after Kyber was selected. They found that in the reference code there was a non-constant time behavior. Here, in all fairness, this was because they assumed that a certain CPU operation is constant time, which turned out not to be constant time. So. Okay, so what can formal verification do for you? Disclaimer, I of course only looked at the stuff that formal verification can solve. You still have to do cryptanalysis of the underlying assumptions. So that is something that formal verification cannot help with. But for the things I mentioned, formal verification can help you to increase trust in the security of cryptographic protocols and algorithms by, for example, verifying the correctness of your security proofs, and also in the security and correctness of cryptographic implementations. So I can use a theorem prover or a tool to actually validate that my implementation actually implements the specification that was given, and this specification actually is an instance of the algorithmic description which I have proven secure, hopefully. Right? And so this might be one way to actually decrease the cost of certification. So if someone comes and aims for certification and comes with a formally verified security proof, formally verified implementation, this means that a certifier doesn't have to check the code anymore or the actually proven statement, right? The only thing they have to check is actually that the right thing was proven. This is still tricky enough, but that can significantly reduce your work. The problem is, right now, I'm not aware of any certification method where formal tools are actually allowed as a proof, which means they cannot even be used as a, I'm not asking to require it, but they cannot even be used as evidence, as far as I know. Okay, as I said, actually when you read formally verified, this is currently kind of a thing that's spread all over the place. It can mean many things, and these are the different things that I mentioned. So functional correctness means that things do what they are supposed to do. You have the side channel resistance and the verified security proofs. And if you're interested, we wrote a whole blog post in the Sandbox blog about this, detailing these things. Okay. And this actually works in practice. So one of the big success stories that formal methods people point out when it comes to actually looking at cryptography is the development of TLS 1.3. Right? So we have seen this whole mess with TLS 1.2 and before with all the attacks. And so when people started working on an update, they said, okay, we obviously have to do something different. And so they started to look into using formal methods to actually accompany the development process and make sure that attacks are found early, and to get some form of assurance of the proofs. So here I should say, I sadly have the slide in the back. What they did was giving a symbolic security proof. So for people that notice, this is an Adolph-Yao model, which is an idealized model. So if you get a proof, this gives you a very limited statement, but these tools actually allow you to find attacks within the adversarial actions that you define. So it can tell you, like, okay, if I have an adversary that can do this, 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 can they break the protocol? And the tool will actually will try to brute force the options of the adversary and try to break the protocol. For a different kind of security proof, which is computational security, so this is what usually the handwritten proofs do, we have a lot of results where we verified essentially all the NIST, the new NIST standards for post-quantum crypto. So we have proofs for Sphinx Plus, the lithium, as I mentioned, and MLChem, and verified the security proof actually in here. We don't have one for Falcon because Falcon doesn't have a security proof at all. So this is something that I'm still surprised how they made it through this process without this getting noticed. So these things take more effort usually, but give you stronger statements. So you get a statement which says, okay, as long as the adversary only interacts with honest parties in the following way, but otherwise can do whatever they like, they cannot break these schemes. But then this is usually based on an assumption, like for MLChem, on some lattice assumptions. And another thing that we recently did at Sandbox was, for example, we have a cryptographic API, which at runtime can change the library that actually implements, for example, the establishment of TLS connections. And this is controlled by a configuration file. And so what we wanted to verify was if you specify, for example, the minimum TLS version should be 1.3, is there any assurance that actually the code that in the end established the TLS connection also really has this requirement on the minimum TLS version? And these kind of properties we verified with the hex tool. Okay, so these tools can give you assurances in that the things that you did are correct. So why is this fun for academics? If you look at cryptography, then essentially what you're interested in, let's see, can I do this here? No, can I do it here? This thing, right? The implementation. This is actually the main thing that you care about. You want to know that your implementation is secure. Which means you want to know that you have certain implementation security properties like constant timeness and so on. So this is something which you want to check or prove. Different tools that some just give you these assurances by the compiler. Others ask you to give a proof of this. And then, as I said, you usually also want to make sure that you're agreeing with some specification, like a standard, which means you have to give an equivalence proof for this. And you have to show that the specification actually is an instantiation of some algorithm, which you have to prove. And then you want to prove some security properties of this. Right? And all these different steps you can actually try to get checked also by a tool. And if you look at the tool suite that I use, which is Formosa, then you have two components, which is the Jasmine programming language, and you have the EasyCrypt prover on the left side. So what you do there is you develop Jasmine code, which is a slightly higher level language, which is quite close to assembly. And that already gives you a certain constant timeness checks. And when you use a compiler, it gives you a certified compilation, which guarantees you that it will not introduce timing issues and it will not introduce memory leaks. So these two things are already guaranteed from the compiler if you do certain checks. The second thing you can do is you can extract an EasyCrypt model of your code, which is essentially a translation just into the EasyCrypt language. And then we usually have a specification EasyCrypt, which we derive from a standard by hand, and have a security proof for this. And then you can give an equivalence proof between the EasyCrypt model and the specification. And often if you have optimized implementations, this is a several-step process, then you first show that these two implementations are actually implementing the same thing. and then like the reference and the optimized implementation, and then you show that the reference implementation actually implements the spec. Right? And this whole process we actually have done for Kyber by now. So this is possible, but it was an effort of essentially large parts of the team, like I think something like 15 people are usually on the papers, and it took something like 5 years by now, I think. So this was really quite massive and takes a lot of time. And the reason for this is that we still fight with certain limitations. So we cannot automate proofs. There is automation, but it's very local and very limited, like most of the stuff you actually have to do by hand. You cannot verify your existing code. So this is more a problem, for example, if you look at the API that we verified. So the only thing that we can verify is actually adjustment code. We're currently working on a way out by building an executable version of EasyCrypt, which would allow us to generate test vectors and then at least link to existing code via testing. In EasyCrypt, we so far cannot analyze complex protocols. And the reason is simply that complexity explodes if you go for too complex algorithms. In theory, this should be possible, but due to the missing automation, this is really tough. And so far, there is a very limited amount of cases where we can actually analyze security against quantum algorithms. So if you're looking at post-quantum cryptography, the results that I showed you before, most of them are actually only considering classical adversaries. And the one point that I mentioned in this list, which is we can actually only verify adjustment code. This is something that, of course, as a person for Formosa project, I'm perfectly fine with this, right? So we provide you this tool. You can check everything that you want. But from a company perspective, if I go to our engineering team and say like, hey guys, this is totally easy. You just do the whole thing again and do it in Jasmine, they will tell me to get lost, and this is not happening, right? So this is something where currently I think a lot of efforts have to go to. So HAX is one approach to do this. HAX is a follow-up of a project called HackSpec, which had the idea to have pseudocode for standards that you can actually translate into formal languages, which you can then further translate into the respective tool languages. And this can by now verify quite some set, or can handle quite some set of Rust, can translate it into a language called F*, and then in F*, you can actually start to reason about security and also about correctness of the implementation. So you can write, for example, an F* specification of your standard, because so far people don't use a formal method for this. And then you can show that that the thing that you implemented agrees with this formal specification that you wrote. If you look at this level, actually, so HAX is mainly a translation tool, and it's mainly in this corner down here. So the security part is not really there. So you can verify Rust code, at least a huge subset. And you can verify functional correctness. This is already there. If you want to verify security claims, you can do certain semantic correctness checks, like the things that we did for this crypto API. But if you really want to go down to things like, okay, Kyber is secure or so, then you actually have to translate into proof assistance again. So then you come up with ROC, formerly called COC, SSProof, ProVerif, tools like this that actually allow you to verify your security proofs. The nice thing is that you have more automation for simple tasks. But the problem with these tools is you can hardly use them alone because, for example, we had several cases where the automatic HAX translation did not work into F*, and then we actually had to work with Kristjan, who maintained this, to actually get this covered. Right? So using these tools on your own is still quite complicated. And one big problem here is also, because it's a translation tool, the maintenance of these bridges is actually quite tricky, because many of the other projects have not enough stake in this, so then for one paper project, they will actually build this bridge and have this translation. Then they continue developing the language, and no one's actually maintaining the translation. So as I said, one big problem is the cost. The other thing is that you actually need experts to run these things. So one way out is that we actually just have the academics build stuff for you. So in Formosa, we're working on libjade, which is a formally verified cryptographic library, which already contains a bunch of cryptographic primitives. We're about to finish XMSS. Sphinx is currently in the pipeline, and Dilithium, I think, too. You have a similar project called libcrux, where the verification is mostly focused on implementation security. So this is by the Crispin people. And you have a few more of these. The problem is you really always have to check in detail what is actually verified. So if you look here, the fine print on the bottom, it says, in every case, please refer to the more detailed notes on verification in each subcrate to learn more about what has or has not been verified in a particular case. So this is, these are still not complete, but this is one way. The other way is to do it yourself. And so for the computational model provers, as I said, this is actually tricky business. So I think we have a lot of people that started implementing Jasmine code. That is not too hard, but actually when you get into proving, the learning curve is quite mean. Like you have a lot of effort until you actually get into the tools and can prove meaningful statements. And if you get stuck, there's not much but asking for help. However, if you manage, you actually get really strong statements. As I said, you get these computational proofs, which give you a strong argument. If the proof fails, you're essentially lost. You don't know if you just messed up or if there's really an attack. What you can do somewhat easily, and I've seen several companies do this, and also PhD students essentially do this with very little effort, is doing proofs in a symbolic model. So there's, for example, Tamarin and ProVerif. These tools are pretty well documented. They have a lot of automation, so mostly you just have to specify what an adversary can do and how your protocol looks, and then you press a button and let this thing run. You sometimes, when the brute forcing gets too complex, you have to guide the proof a bit. But it takes a lot off your shoulders. And so here the nice thing is if there's no proof, then it actually gives you an attack. Right? So the thing is, if it doesn't find an attack, well, it just means that with the whitelisting that you did, this attacker cannot attack the scheme. But maybe if you give it more capabilities, it can actually attack it. This one I should have moved earlier. So the limitations that we have for the computational tools is the effort, the expert tools. If you write new proofs, you often need help from the actual tool developers because the things might not go through. And you always have this trade-off between little automation or somewhat weaker results. And there's really hardly any integration between tools. So you actually have tools for different use cases where they are really strong. Like you have tools that work very well for protocols. You have tools that work much better for cryptographic core primitives. But actually using them for different parts of your argument is pretty tricky because you cannot just translate from one into the other. And the most tricky part, especially for these symbolic proofs, is these statements must be verified. So for example, we did a proof for PQ WireGuard. We forgot a semicolon, the proof went through, everything was fine, and then at some point the Tamarin people were like, hey guys, there is a mistake. But by the way, you're lucky because it still goes through. But this is something, because of a missed semicolon, you might potentially prove something entirely wrong because your adversary is too weak. So in summary, we do have these tools to actually get really strong results. For example, for Kyber, we have this full verification. But actually doing these proofs is still research. We need some improvement on usability. But I think if we have these tools, if we have these proofs, then they are actually strong arguments that should be considered in certification because they can give you assurances that reduce the amount of effort that you need. Yeah.
Thank you so much, Andreas. The last sentence that he said, I think that was the most important one. If you ever see a well-published paper that somebody has written a full formal verification on something, a product or anything, and the conference seems to be reasonable, then that's a good argument. But then, like with certificates, you have to go and read what was the scope of the verification.
Yes.
Exactly. Thank you so much, Andreas, again. Next up, we have Petr. And Petr is telling us about a different kind of tool set. So this time about how to work with certificates more easily. Please.
And not only that, I also stick with the title done, created for me. And it states breaking the Estonian ID card. So I will talk about what it took in 2017 to do it and what would take it today and if we are better off with respect to tooling we have in hand. So we are a small lab in Czech Republic, in Brno, quite far away. So how we learned about Estonia? At least for me, it was, I knew just one Estonian before from the open source community. That was Martin Paljak there. So how we get to learn all the people here in the room. So roughly around 2014, we already had a bunch of smart cards in hand, and we wanted to know how they are implementing RSA. And that's a tough job because the vendors are not telling you how this is done. So we had the idea, let's take all the cards we have, run some tests on them that are somehow probing the implementation, and then take also a lot of open source libraries, run the same tests, and maybe we can spot some similarities. And based on that, we can reason if this card behaves very similarly to OpenSSL, maybe they are implementing the same way implementation, and maybe we can find some bug there. So for that, we started to generate over the several weeks RSA keys directly on cards. So we end up with like 60+ million keys. But we were not really finding vulnerabilities, unfortunately. We got a lot of interesting pictures that were visualizing the way how we were looking at the properties of the unknown implementation on the card, but no bugs. But what we found was these pictures are not the same. Despite the fact that like RSA is reasonably simple, we were not seeing the same pictures. And we were wondering why. And then we realized, okay, it's because, also based on the open source libraries, they are using the different way how to generate primes. And because they are ending with slightly different structure of the primes, we can observe that even in the public keys. So actually the result we got out of that was we will take a public key, we will look at specific bits, and we can say which library or which card generated these bits. This particular key, sorry. And based on that, so it's basically attribution. You will look at the key, and you know it's from OpenCell. You will look at the key, it's from Infineon, okay? Not really bug, it's like maybe information leakage. But there was one source that was more different than others. We were even like joking that like these strange keys. And we kept making new pictures. And at some point, we came with another picture where it was like really strange. And all the previous pictures were like, okay, they are just doing it differently. But this picture, I will not get much into details, why it's that, but it was saying, okay, the primes from Infineon are having very specific algebraic structure. And just by observing that structure, we were able to get exactly the format of the structure. So what do you expect in ordinary implementation? Primes are random. What do we got for Infineon? This formula. So they were generating it this way. So that itself is still just information leakage, but it turns out that it's vulnerable. And while, say, random 2K bit keys shall take these huge amount of years to factorize, it turns out that Infineon was way easier to factorize, 140 CPU years. And that's still a lot of years, right? Like so is this a practical attack? The problem is that the factorization, the attack is perfectly parallelizable. So if you have 1,000 cores, you are doing it 1,000 faster. So then it burns down to who is using the chip and how much you are paying for the energy, right? And it turns out that, unfortunately, Estonia was using the chip. So that was in 2017. We notify Infineon, then we also notify Estonia. And over the years, the expected price for factorization is below $1,000. So I would say that's practical. So that was in 2017, and that got us here. But the question is why we, at the end, got to the situation that we were not knowing the fact. I will try to use the pointer. Oh, doesn't work. That such formula is inside the card. And the problem is, of course, that everything was closed. But if you will go back to 1997, there was a nice, shiny platform that was called Java Card. It was by Sun. It was open. I see Eric smiling. And this is, I think, the first prototype. So by open, it's important to say what it means, because Java Card API was open. So you know the implementation, you know the methods, but you don't know the implementation. So how it's done, that's not open. And such card is, such implementation is inside the card with some nice picture. On top of that, the chip itself is actually just 3 to 3 millimeters below these contacts. And inside that, you have rough understanding what's inside. There is some CPU, some random number generation, some memories. There are also some cryptographic accelerator circuits, some implementation of libraries, but much is unknown. Like details, exact details, how it's done, that's unknown. And the reason why is that there are multiple of them. IP protection for vendors, like hardware, making hardware is expensive. Also, certification requirements. They are saying, okay, if you like to certify, you need to reach some security level. And for that, you need to show that it's very hard for an attacker to break the card. And if you will not give any free samples to academic researchers or the world, it's harder to break it. And therefore, people are motivated not to give samples for, say, independent analysis. So we don't know many things, like design, layouts, packages, implementation, and so on. There's also vendor API. Some part is public, some part it's not. So then the question is, who is analyzing the security of these parts? So we have this chip, who is looking for the bugs inside? And there are certainly people that are looking. But these are not end users, these second parties, right? Because the typical end user holding the card, they lack the skills, they don't even know what was tested, so they basically outsource the work for certification schemes, laboratories, vendors. Okay? So vendors, they have great understanding of the implementation. They did it, right? They have also frequently advanced methods, hardware. They might have some limited knowledge in security testing, but still they have like great knowledge, but they have a conflict, like the time to market versus let's say analyzing it a bit more to be a bit more secure. Schemes are typically mandating like common criteria to use some independent evaluation laboratories. They have a great knowledge. They commercialize the process of testing, so they know how to do it reasonably fast and on time, and also on budget. They might have a conflict between the tough analysis and keeping vendor as a customer. Because if you are too harsh and you are spotting too many problems, the vendor might go for some other evaluation laboratory which is less, let's say, sharp on this. Also, if the evaluation laboratory will find some problem, the vendor can either fix it or just put it out of scope. And that we saw that several times as well. So then we have the scheme like BSI, ANSI, NIAP in US. They do have some experts. They are typically not involved directly in testing. They shall be impartial. They tend to have stronger ties to bigger players. But okay, so these are four parties that are typically involved. What would be the ideal setup for finding bugs? First, perfect knowledge of design, implementation. So basically white box testing. So that's great. Also, you need to have competent people, equipment, all these things, knowledge in testing. And you need to have a lot of time for that. Okay? So where academia, and let's say independent researchers fits into this part, we are definitely not perfect case for this, because we have small understanding. We typically work in a black box model. We don't know how it's implemented, design decisions, nothing like that. We may have some great knowledge in some advanced attacks, and we may have some equipment, but not like covering everything. Evaluation laboratory knows, okay, these are the steps. We need to have expertise and hardware for everything. At university, we'll have just some subparts, maybe deep, but some subparts only. We do have a lot of time, that's good. But we have also bias. We tend to look at the more complex results because at the end we need to publish. So just buffer overflow will not do it. So we tend to go for like fancier attacks. Another thing is evaluation laboratory is contracted to do analysis of one specific chip, whereas we don't care that much about that part. It's actually harmful for our method to do so. We are more focused on wide-scale testing, like take a lot of cards. So how difficulty of analysis of these cryptographic devices evolved over the time. In the 90s, we got these fresh and very powerful attacks based on side channels, this simple power analysis, differential power analysis, and so on. Like really, really powerful attacks that were coming mostly for academia, quickly turning into some companies and some protections being patented. At that point, it was very difficult for us to get any card. So basically impossible. So the industry making cards, they were heavily relying on black box and also not giving free samples. Common critical certification was already there. It was providing some level of information what was tested, but it's best what you can get still nowadays, but not deep enough. You will just have the mention, this chip is tested against the differential power analysis, but you will not know how exactly, with what results, how many traces, nothing like that. That's everything is kept out of the public visibility. And at that point, definitely, we had no open source tooling, nothing, no like major open ones people can widely use. Okay, so there's a picture with respect to extraction. So you can get the card. If you can get the sample, you will measure some side channel, maybe power side channel, maybe just timing side channel. And if you're lucky, you will get the key out. So let's say roughly 10 years after, the situation changed. Already at that point, the vendors and laboratories, the evaluation laboratories had advanced setups. That was great. And even us, we were able to get some samples of cards. Typically, just like second-hand cards, usually going from China, we were hoping that they are matching what is real in a real world for the electronic IDs, for example. But at least we were able to get something. There were practical applications of more advanced attacks, so say lattice-based attacks on ACDS, ACC nonces, and so on. And there is a growing open source community. So things like Chip Whisperer, like people that were making the hardware plus software around that allows you to plug the chip in and do some analysis. So that was definitely growing. Okay, since then, what changed? Deep learning made a let's say, big attack of the domain, because it turns out that you don't need to really understand how exactly the traces are constructed. You can just train a neural network, and it will extract the interesting part for you. So that's good. Improved lattice-based attacks. Academic researchers were looking into all of this for a long time, but typically they were working with white box targets, because if you are in academia, you like to publish, so you like to design and show, I have this algorithm, let's say AS. This is the vulnerability if it's not protected. I'm suggesting this protection. I'm implementing this protection. I'm measuring it again. I'm showing that you need to have 100 times more traces, so it's way more difficult to attack. So you want to have a controlled way, right? So you are working with maybe FPGA where you will implement everything, but basically that's a white box target. Not that many people were working on the black box ones for the real smart cards. And we are still stuck with having cards that are 2 generations back from the state-of-the-art ones. So our way, in our laboratory, how we are studying these devices, we basically figure out that, okay, what works for us is the following. We work with the black box targets. We will first design a technique how to probe that target. It can be looking at the particular part of RSA key or looking at the particular part of nonce in ECDSA signature. We will implement the open source tool, and then we will run it. And we will run it against as many targets as we can get. We are not just picking one Estonian card and trying to do it there. We are trying to run on everything. Libraries, hardware, everything. And if we will start to see something off, we are starting to reason why it's there. Sometimes we will get the knowledge about the internal implementation, and then sometimes we will get the publishable method and maybe vulnerability. So the ideal outcome for us as academic researchers is we can have the method published, so we have some reasonably complex and interesting method. We can get it published. We can demonstrate real-world impact. And we can also, because we are working in a black box analysis paradigm, and we have open source tools, and we are not tied with non-disclosure agreements, we can just publish these tools, and other people can use it as well. So typically, the steps 1 to 3 are reverse engineering, and only then in step 4, it's the attacking part. Also, the step 3 is important, because that's a step that is increasing our chances to spot something interesting. Because if we are just analyzing one card, chances are very low. It's not that the card is without bugs, but we will likely miss it. But because we are doing 30 targets, likely we will hit something. So it works for us. And it worked with ROCA and with other subsegment vulnerabilities as well. So this is a table, don't try to really read it. I try to compile to the table of attacks that actually attack the real smart card or real trusted platform module. So not just like very nice theoretical attack, but something that works with the practical hardware. What is important here is this goes from 1996 to this year. And if I will, okay, I lost colors. Okay, now you can see it. I can't see it here. So if you will see who did it, basically who was responsible for finding that, you can see that initially it was mostly academia. Then the orange, so blue academia. The orange one are, say, independent evaluation laboratories. By independent, I mean they are not signing NDA with the vendor, and then because then they can't publish. So external laboratories, and then the green one are the vendors itself. Yeah, so it seems that there is some trend towards external laboratories and vendors publishing the vulnerabilities, but still academia is responsible for a large part. And you can see clearly the bias here, right? Like we are working in a black box model, which is supposed to be the hardest one because we don't know the design, we don't know the implementation. Yet the academia is responsible for most of the bugs found, at least publicly, right? So there is clear bias. So how is that? And my theory is that basically the public information that there is a bug is basically a side effect of academics wanting to publish and external commercial laboratories wanting to advertise themselves, because then they can show, okay, we are really good, we found this problem, hire us for subsequent work. Rarely it's vendor itself, and actually out of these 3 or 4 green parts, Yubico was responsible for most of the reporting for the bugs they found, and then they reported and filled the CV for that. So vendors don't really like to do that. It was mostly Yubico. Then the question is, how likely is it that with a black box analysis, we are finding almost all the bugs that are there? And of course, I think it's very unlikely that we are finding all the bugs. So likely we missed a lot of problems, or we neglected them because maybe we were on the right track. But because there were 2 layers of defense, and we just managed to go over the one, but we were not aware that we went over the first layer of defense because there was another one and that stopped us. We just said, okay, it seems good, but actually there was a problem and one layer was breached. Also, I believe a lot of problems are simply undisclosed, right? They are found by vendors, they are found by laboratories before the product is released. And that's perfectly understandable, right? Like we are testing something, we are trying to make sure there are as little bugs as possible. So I'm okay with that. But I'm not okay with the second part where it's already deployed, people are using the device, and then someone will find the bug, will not publish it, and then the vendor will decide, will I fix it or not, or will I silently go over, right? There are also publicly reported vulnerabilities, but with a low visibility, which means, yes, they were reported, but the typically vendor decided, okay, we will not file CVE, we will not make a public security bulletin. One example might be the bug we found in Intel firmware TPM. It was enough to just gather 9 signatures, and then you can get the private key out. And you don't need to even actively observe the creation of the signatures. Just later on, you will get the signatures. Like, pretty bad. But Intel said, OK, it's outdated product. We will not do anything about that. So now I'm getting to the part. If we would go to break Estonian ID today, what we can do, whether we are better off. So first of all, we are no like special announcement here, like we were, so that's one thing. Second thing, as I described, we would not do it because it's the likelihood of failure would be too high for us, right? Because it's very unlikely that for one target we will find the problem. We will miss a lot of problems that are there, but unlikely that we will hit something. So we would like to, as academic researchers, would like to go some wide range testing. But anyway, I will try. So first, you need to know what the Estonia is using. You will use Google. RIA is doing a good job like documenting what they are using. So you can find it. ID Cosmo. So you have the at least identification of the chip. That itself might be just expected for you as Estonians. It's not really true for Czech Republic, right? Like finding what we are using is not that easy. So then, because you know the platform, you can open the common criteria certificate. You will just clean your French language skills, and you can start reading. Okay, so that's you will get a lot of information out of it. You will still miss crucial ones. So you will then want to like dig deeper. The tool Waszek was mentioning, SecCerts, we built this tool for ourselves. We wanted to have something where we can search certified cryptographic devices. So we basically took all the PDFs from common criteria and FIPS. We extracted the mentions about certified devices there, specifically their identification, like for BSI, it's starting with BSI minus, for ANSI, it's starting with ANSI, and so on. So you can make regular expressions, and then you can start to search for the certificate for Estonian ID. You will find it, and it's there. Because we use the regular expressions, in contrast to, say, ChatGPT or AI, we know pretty well that the likelihood of false positives is low. Right? So we know what this is doing. This is like a simple method. So that's good. you will get at the end something like this. So the graph is too small for you to read, but basically the Estonian ID runs on the platform that is referencing certificates issued for the hardware platform below it. And these are these two ones at the top, these outgoing. And then you have a lot of incoming, which are the certificates that are referencing Estonian platform. On top of that, you can see that there is a lot of yellow, and yellow is not where you like to be, because this means these certificates are already archived. So they are out of their typically 3 to 5 years period. Estonian certificate, let's say for the Cosmo platform, it's still green. It was extended. But hardware below is already archived. A lot of things that were certified later on is also archived. Doesn't mean that it's a vulnerability, but it means maybe people are not paying any longer attention to analyzing these platforms below that much. Okay, so that's one thing. Second thing is, this is not what the kids nowadays would do. They will just ask ChatGPT, right? So I asked, and it works pretty well. ChatGPT can tell us it's Cosmo platform. It will tell you like it's 8.x, because they will also tell you the whole history of the Estonian platform was built on different chips. And so that's great. But you may wonder, like, is this hallucination, right? Fortunately, you have resources, so you can check. So I checked, for example, here for the Rocca one. There is a resource and reference to Arnis Parshov's paper on Usenix. And I believe this is why the ChatGPT is giving you like really good results, because Arnis like summarized everything very nicely. So this is easy to get. Within 1 minute, you are getting nice setup. So that's one thing. Second thing is there was vulnerability, and we can start to check about that vulnerability, because coincidentally we were the ones who found the Rocca vulnerability. So we can just now compare, right? On the right, you can see the reasoning mode. It's like searching the internet and thinking, okay, I found Rocca, I found UC leak. I also found some other attack. Does not seem related. So it's really interesting. At the end, it says, for Estonian, I have these two, for the Estonian ID, based on Infineon platform, which is not the most recent one, I have two relevant attacks, and we can start to now verify what's there. So Rocca and UC leak. This is like the summary, what the ChatGPT will do. So let's go it bullet point by bullet point. So root cause, it got it right. Like the problem is it's generating RSA based on the prime templates that are not correct. Then we have one fail here, because it says it affects only keys generated by the chip before November 2017. And that's maybe not completely fail, but it's very misleading, because it does not really tie to a time. It ties to the version of the library that runs on your card. I can still take a card and generate vulnerable keys nowadays. Although the second part is correct, if you import it from outside, as you learned as well in Estonia, that you can import into your Estonian ID cards from outside the chip, then it's safe. Then it's also like not really nuanced with respect to mitigation and so on. It suggests some mitigations. So audit, that's good, that's correct. We have some hallucination here, because it's saying force 3000-bit ECC. Okay, so that's a bit too much for current standards, but I think basically it almost got it right. It likely thought 3000 RSA or ECC. But okay, so this is something where it can get wrong, but all other things are correct, and especially the last one, that you shall be prepared for the bugs like that. Okay, I'm going to the last part, which is saying, okay, we have some custom-built expert tools. That's good. We have ChatGPT, and people will just go for it simply because it's easier. And we are building the expert tool for 5 years, and we are still struggling with user interface. Like ChatGPT got it right. The problem is here, of course, false positives, false negatives, and nuances that are getting here. And this is a problem not just for end users, but also for vendors, because then the summary is out of their control. They don't know how exactly this is expressed. Also, initial information needs to be there at the first place. That's also important. I will skip this slide. The crux of this is if I would like to nowadays do analysis of Estonian ID, I can't, simply because I can't get the samples of this card. I can get them if I will sign NDA, but then I can't publish results. Okay, so it's a bit problematic. So how to improve the trustworthiness? Eric was mentioning that during the talk we have a bunch of options. Authority was tested, and vendors and schemes were doing a good job to increase the basic baseline. I would like to see more end-user verifiability, where end users can actually verify for themselves. And I like to use the wisdom of crowd. Okay, but this can be messy. I will very quickly show how this can be done. On one side, on the left side, we have certified products. On the right side, we have people doing various analysis, ending up with metadata about the keys, but also description of the truly random number generator and so on. So what we can do is Infineon can say, okay, I have this chip. Okay, this is a small package. I have this chip, and I will sign that JSON blob. Then some random guy will come and collect the keys and sign metadata with these keys. Then our lab will tie these together. So they will say, okay, this metadata ties to this particular product. Everything is signed. We can do more. Then maybe Maitre, as responsible for CVs, will come with another blob, also tied together, because at some point there was a ROCA. Maybe RIA at some point run ChatGPT, analyze the summary and say, okay, this is pretty accurate. We'll share the summary of that thing. And because Infineon is happy with that summary, they will create the binding and sign it as well. Okay, so that's the basic idea. And then you can go and, as an end user, you can filter. And the problem is who will build the system, right? Fortunately, we don't need to build it. It's already there. It's called Noster. And you can filter based on the key. So you'll just say, I trust Infineon, I trust Maitre, everything else, I don't care. And then you will work on that. And I will stop here. Thank you.
Yes. So let's thank the speaker. Amazing. Amazing.
Thank you. I got still 26 minutes.
No, that's the coffee break. But you can find Petr, and please also find Andreas over the coffee break to ask them about tools. And yes, it's the coffee break. We have been amazingly on time until now, so let's keep to that. In this last block of the day, we'll look a little bit on collaboration and how is the discussion across countries and across oceans important. So first off, to start this, we have Kersti Piilma from the Estonian National Security Authority. Please.
Thank you. It's really a pleasure and honor to be here. My name is Kersti Piilma, and I'm the director of Estonian National Security Authority. This institution in itself has traveled a long way, being originally established in 1995 under the State Chancellery Bureau. It ended up broadly speaking, under the Ministry of Defense by now. We will come down to that and our responsibilities after a couple of slides as well, and go deepen and deepen where we stand and what we are responsible for. Let us continue. First of all, I'd like to introduce the basic principles and ecosystem of protection of the classified information, because that is exactly what Estonian National Security Authority is also to some extent responsible for. So in the domain of information protection, we usually come across to different layers of information. We have provided information a certain classification standard. We have noted down that some information needs more protection than the other information when we talk about state information. It is quite usual that people from every domains of private domain or just in everyday activities, we come across only to public information. And then there might be public articles discussing about classified information, but in reality, the discussion only goes up until security level that we call unclassified information, which is an information which is only for official use only, meaning that it has some limitations of distribution. But it is not yet classified information. So every domain, as I mentioned, in our security-wise, we need to determine what type of information it really is, how much it needs to be protected. And classified information is indeed only information that is officially stated that is restricted, confidential, secret, or top secret. And usually in the state domain, then need to have a specific trust vis-a-vis, is it a physical trust dimension, is it a personnel trust dimension, or IT security involved to come across to such a level of information. So, to continue, where is in Estonia, who is responsible for what type of information protection in Estonia? Usually during previous conferences, or at least last year, I know colleagues from Data Protection Inspectorate, Information System Authority of Estonia were present. So they are responsible for protecting rather unclassified information, including Consumer Protection and Technical Regulatory Authority in Estonia and Data Protection Inspectorate. So these are the authorities responsible for not classified information. The not classified information part, it usually, when we talk about for official use only, then we have the usual standards that apply for the information protection that are well known. Also here today referred, coming from European Union, like NIS or standards like that, but we usually don't come across to classified information protection standards. Some countries have publicized them. Like in Estonia, we have a specific legal framework that is mostly read by anyone if they are simply interested in, but not deep down into when it comes to cryptography. And vis-a-vis the authorities now responsible for the classified information protection here in Estonia, there are mainly 3 different entities that are responsible. First of all, national classified information in Estonia, the distribution and oversight of this information is protected by Estonian Internal Security Service under the Ministry of Internal Affairs. Then secondly, we have under the Ministry of Defense domain, two actors, which is first of all defense forces, where they protect the national classified information within defense forces. And then we have Estonian Foreign Intelligence Service, where we have different mandates for the protection of classified information. First of all, we have their independent decision-making body called now Estonian National Security Authority, which is responsible for protection of foreign classified information. That means that where foreign countries, including European Union or NATO, has decided to share that information with us, then we need to provide them assurance that this information is kept really secret. Then within Estonian Foreign Intelligence Service, there is also different authorities which are responsible for the protection of classified information within IT systems, classified IT systems. And there we come down to the function of cryptology and the importance of cryptology for the protection of the most sensitive information. And Estonian Foreign Intelligence Service is also responsible for protection of all sorts of information, either foreign or national information outside of Estonian borders. So three different functions. But today I'll specifically highlight the cyber part, or the cryptography part, and where we all stand in this scheme. So, as I highlighted already previously, it's not only about technical domain that we worry in the context of classified information systems. We also care deeply about the personnel security, about the security of information, meaning that from which moment the information was created and where it will be ending up, what is the whole life cycle of the information. So by that we mean the security of information. Then we are worried about the physical security, where the IT system is functioning, whether it is in the secured area or in an administrative zone. Then we specifically regulate also the part where industry or academia comes across with classified information. Then there are specific rules for that. Companies need to be vetted. That means that there needs to be a security control done vis-à-vis their personnel who is there, etc., when there is a need to know for companies to come across with classified information. And then the cybersecurity in itself, which has then different parts that we consider very relevant. But I will come down to that as well later on. I will also flag quickly the legal framework in Estonia that is present for the protection of classified information. As mentioned before, there are a couple of publicly available acts. One of the most important one is State Secrets and Classified Information of Foreign States Act, available at our Riigi Teataja portal. And there you have a specific annex, addendum 14, which states clearly the requirements for classified information, communication and information systems. But that part does not regulate cryptography in a very detailed way. Cryptography is regulated by already documents that in itself are restricted. So I'll not come down to the content here. There is also Tempest-specific requirements that are also restricted usage. Then what is binding us in protection of classified information is also the NATO and European Union or other international organization security regulations. Here I mention the European Space Agency, for example, and those we have to oblige. We have to see that all those requirements are met when protecting the information coming from those organizations. And when the topic of my presentation is why security or why certification evaluation matters, then of course it matters because in those regulations it is stated that you have to basically approve and evaluate the products that are used in classified information systems. Then I'll flag quickly also give an example of different protection levels for different classified information. Like for restricted, we are not as usually as strict, of course. We are not paying much attention to the personnel security, meaning that the persons dealing with restricted level information are not security vetted. We are not doing extra check from where they come from, etc. While confidential and above information definitely has a strong element of personnel security, of physical security. Both of the elements have restricted and confidential and above have requirements for electronic processing of information. And highlighting those two requirements here, as stated before, all information that is classified basically needs to be in an accredited system and using approved encryption. Now, exactly going or coming down to more specifically to this domain. So within Estonian Foreign Intelligence Service, there are specific authorities present foreseen by our law. And one of them is called Security Accreditation Authority, which foresees clearly whether the computer system in itself has vulnerabilities. And then there are two crypto domains. One of them is the selection of cryptographic products, and the National Communication Security Authority, or otherwise known as Crypto Approval Authority in the EU context. These are placed also in Estonian Foreign Intelligence Service, and they are, or this entity is responsible for exactly for selecting and a right product. And now we come down to Kristjan Krips' presentation a couple of presentations ago, where he mentioned that yes, Estonian MOD, together in reality with also Estonian Ministry of Justice and Digital Affairs, has really asked the academia and academic environment more broadly, like also Cybernetica and Metrocert, to provide analysis on this topic that was just introduced to you by Kristjan in depth. But flagging that we are behind it in a context that we really need to build this measure up within Estonia. For the reasons, first of all, of just meeting the requirements. We can always be dependent on foreign evaluation bodies, of course, but the rather trend is to become more independent in this field, currently also in Estonia. And yeah, I'll touch upon the cooperation moment a bit later. Continuing now with different authorities. National Distribution Authority. It's also responsible for crypto, but from a different angle. It's responsible for basically for the supply chain security of crypto materials used in classified systems. Because crypto material, when it is produced, it needs to be really kept under close protection. In this our context of classified information protection. Then National Tempest Authority is responsible for confidential information and above, for the protection against electromagnetic emissions. So we also have already a laboratory present in Estonia, and that laboratory then takes care of that threats emanating from that threat vector. Then technical security countermeasures, meaning eavesdropping, or that people don't hear what you're saying when you are so that the threat actors would not listen to you, what you are talking in a secure environment. So this field deals with that. But in a crypto environment, most important in this context is the, as mentioned before, so-called Crypto Approval Authority or National Communication Security Authority and National Distribution Authority. So Estonian NCSA, meaning the National Communication Security Authority, it does approve cryptographic and communication security solutions for classified information systems, and there is a need for an evaluation methodology for communications and cryptographic solutions in order to use them in classified information systems. Then international cooperation has done promise that we will touch upon this issue. I will do that as well, just to tick the box. Indeed, Estonia participates in the classified information protection area in different forums, specifically in EU and NATO context. There are working formats addressing the information assurance or TIS security, different labels used in one or the other international organization. Cryptographic security is one of the highlights there. The discussions are not open, but the cooperation is ongoing in that format. In the EU, I'd like to flag that there is a specific appropriately qualified authorities group called the AQUAS. Only these European Union member states are part of that highly qualified group who provide second evaluation for all cryptographic products then used for the protection of secret and up level of EU classified information. Then, indeed, in those formats, Estonia is providing its input vis-à-vis when it comes to requirements, specifically whether we find those requirements in the crypto field to be too demanding or less demanding. So this is the work that we do there in those formats, basically setting the rules for this whole communities. And then there is one more element that I'd like to flag is that in the confidential and restricted level of information protection in the EU context, it is given to the member state themselves, to the Crypto Approval Authority, to approve those products. And as we have seen now, European Union is definitely very aggressive in due to the current threat picture to have as many private companies involved in developing new technologies. And very soon those defensive technologies, they become already classified information in themselves, and those there is really a need for new products EU-wide to protect that type of information. So if Kristjan was highlighting that there's only one or two products to be certified or in need of certified, I think that definitely the market is wider when we talk about the EU in general, and also in Estonian context for protection of restricted level information. I would also see more need and vis-à-vis our defense forces as well. So I'm a bit more positive towards the need. Then indeed, this information you have already seen from Kristjan's presentation, just again to highlight that indeed we initiated this research and development project to develop Estonian national evaluation just at some stage at least, and we are trying to make it really strategic and to tackle also with the issues of education. But there, I think we are still in the baby steps. But nevertheless, you need to take the baby steps in order to grow. So, and my last part of my presentation will come down to, again, providing more detail on why do we need to evaluate and certify. I flagged that there is, first of all, a requirement coming from all those regulations, a need for, in the context of classified information, to evaluate and certify products. But of course, there is a threat factor part there as well. And we see a clear interest, of course, from the persistent cyber threat side, from hostile intelligence services, targeting our most sensitive information. And in this regard, I just have to warn you all, because you all are targets as well. This is definitely, it does not include only interest towards classified information, but also unclassified information. And then there is another, technology-wise, of course, well known to you all, the quantum computing element. Potentially, we see it as a possibility for adversaries to collect large volumes of data today, and then they intend to decrypt it in the future. So we see rather that the post-quantum cryptography would provide solution here than the quantum communication part, perhaps. But we will see. Hopefully, you will provide here also more information and in-depth analysis. Then the evaluation in itself, we find it provides a very good element in regards to supply chain security. While evaluating, while we have a scheme of evaluation in present, we also pay much more attention to producers' background, and I think that is one of the ways forward. Last, to sum up, indeed, we think that evaluation and certification is rather a positive thing, and see that as a solution in the Estonian state context. We hope to receive as much support from the academia as possible, but while remaining just aware of the threats also in this domain. Thank you. Any questions from?
Let's thank the speaker. Daniel has a hand up, so can we get a microphone?
Thank you. Thanks. A question about the cryptography. I mean, it seems to me like you are considering like the classified and unclassified information domain separate, which, I mean, from an informational point of view, they are. But good cryptography is good cryptography. Like, it sort of sounds that by focusing or differentiating between the two categories, you're doing something similar to the GSM encryption, so where for export there was a deliberately weaker algorithm. So if we have good cryptography, it will protect all the information the same. So why are the processes different?
I personally have been trying to promote that idea within all relevant for us. I think that first of all, we need to see that the information itself needs to be protected. So I'm definitely for that. Currently, we just have regular legal frameworks that have separated the two domains clearly. The first initiative, I would say, in a broader way, is done under the European Union currently. There is an information security regulation just being drafted. And this regulation, as a first step, tries to encompass the two parts and put that under one umbrella. Of course, Ministry of Defense in domain in general is responsible rather for the classified information protection, so I can only speak of that. But in the Estonian context, I would say that, of course, also from the EU Cyber Security Resilience Act, starting from 2027, there might be a need for certification indeed for the unclassified products as well. So I would definitely in for having one united view on all and good cryptography protects us all.
Okay, thanks.
Yes, please.
For ideal protection, does every state needs to have own cryptographic products? Or where is the balance?
Well, that's a political issue indeed. That all those ideas, they come from the geopolitical domain. You know, if we see that you cannot trust the other country or the other institution, then we must change the policy. But in general, I think NATO in itself has done a lot to having created this one bubble, and the EU the same way. So, yeah. But, you know, when we follow the news currently, it's not always clear who is your friend and who is not.
Yes, gentleman there.
Sorry. Quick question. The digital embassy in Luxembourg. Any specific challenges that you faced in regards to protecting the data? Were there any like specific separate approach to that, or was just like general approach? Thank you.
Thank you for the question. I think that should be addressed rather by the Ministry of Justice and Digital Affairs, but because we do not have there any classified information.
And we're done. Thank you very much. And as the last speaker to the day, we have Luís from NIST. We're super happy that you came. Now you've heard for the whole day how Europe has set itself up. So now we can hear how the US is tackling the modern challenges. So knowing from the background of what NIST does, then there's a lot of exciting, very futuristic cryptography being worked on there. So there's going to be some focus on this as well. So very excited. Thank you.
Thank you very much, Dan, for the introduction, and thank you very much for the invite to be here today. I'd like to start by clarifying my affiliation. So I'm not an employee of NIST. I'm a NIST associate, and essentially I'm a foreign guest researcher as a contractor. That said, I have been close to NIST since 2017. I've worked in a number of projects, so I will be presenting my personal perspective and part of the work that I'm developing, namely some things related to future cryptography. I also wanted to mention that my background is more on the side of theoretical cryptography, namely MPC, so I'm not so much familiar with certification. However, the topic of this presentation today is about work we're doing to promote future cryptography, which does raise a number of challenges and opportunities in certification, so I think it's a good venue for exchange of ideas. So in summary, I'm really glad to be here, and again, thank you for the invite, and we really appreciate this spirit of collaborative sharing of knowledge. I only used ChatGPT to get some translation because I wanted to include some Estonian words just to thank you in your own language for the invite. And just to start, I usually like to present a little bit of a roadmap of what are the goals of the presentation. So experience has been showing that it's actually usually useful to present an introduction about NIST because there's a lot of myths of how NIST works. So, you know, a little introduction, I think, does good when people actually are not very familiar with what NIST does in terms of cryptography. Then I want to take the chance to disseminate what we call, in short terms, the threshold call, which is essentially an expedition into what we sometimes call advanced cryptography, but for the sake of today's event, you can consider this an expedition into future cryptography. And then I'll try to make a few remarks in the time that is available on a few topics that are suggested by this endeavor, topics that are of anticipated interest, you know, with respect to certification and things alike. And also the slide deck will be available. It's a usual question. Okay, so let's start off with an introduction about NIST. So the National Institute of Standards and Technology in the US is what we call a non-regulatory federal agency. It's part of the US Department of Commerce. And being non-regulatory means that NIST does not regulate who needs to follow standards. There are then other agencies that may in some cases issue regulations saying that in some circumstances people should use NIST standards. There's also a lot of cases where private sectors decide to voluntarily follow NIST standards, but it's not the NIST job to create those regulations. The NIST job or mission, if you will, involves a number of keywords. You know, there's a statement here, I selected a few. In particular, it involves creating standards. NIST is a fairly large institution, relatively. Numbers from about 2 years ago, it has about 7,000 staff members. It's organized into laboratories, divisions, and groups. And if you focus on the cryptographic technology group, which is where I exercise my activity, we are part of the information technology lab, within which there is a computer security division, and then within which there's a cryptographic technology group. This is really the group that works on the standards, you know, like PQC, lightweight cryptography, also the threshold call. There are other groups of adjacent interest, like, you know, to do testing and validation, but I will focus on the work done in the cryptographic group. So we sometimes characterize the activities in terms of you know, doing standards, doing some research as well, and doing some applications. Please don't worry about the acronyms. This was just to fit here. That's a lot of acronyms, but this try to represent some of the projects. For example, starting from the left, RNG, random number generator standards. We have post-quantum cryptography, multi-party threshold cryptography, lightweight cryptography, privacy-enhancing cryptography, hash functions. On the downside, starting from the left, we have, for example, interoperable randomness beacons. That's a project that is not so much about doing standards, it's more like an application and a kind of a prototype. We do some research on circuit complexity. We have standards on elliptic curves, digital signatures, block cipher modes, key management, etc. The output from NIST to the exterior is usually in the form of public documentation. So FIPS is what Federal Information Processing Standards. Those are really known as standards. They need to be approved by the Department of Commerce. But there are also a lot of standards that are approved via special publications, which just come out of NIST work. We call them SP 800 series, which means special publications in computer security. And then we also have a number of reports that are reports about positioning of projects or research results, preliminary results, etc. And we strive to do this with international cooperation, you know, in the least because all these publications are open for public comments, and so, you know, we regularly interact with government, industry, academia, and other standardization bodies. Just as a way of, like, kind of a little bit of an update, here are some example recent publications. Actually, there's a little typo. The FIPS should start on 203. So these are the recent PQC standards for signatures and the key encapsulation methods. Also, the Lightweight Crypto Project has published an SP that selected a new pseudorandom permutation that is useful for block ciphers, authenticated encryption, hashes, and extendable output functions. We have a recent SP that gives recommendations about key encapsulation methods. There's a report about PQC transition expected by 2035. And there's also, I call your attention here to the before last one, the 8214C, which is a report on the threshold call, and that's going to be the focus of my presentation. There's also a recent report on requirements for an accordion mode. It's going to be a new cipher block mode. Okay, as I mentioned, there's a variety of crypto projects, and just to pull a few to make a little bit of contrast, here are two examples that are rather popular, so post-quantum crypto and lightweight crypto. These are projects that have been developing a standardization effort where, from the start, they knew the type of primitive that they wanted to standardize. They opened a process whereby the international community made submissions, proposals for what would be the best standards, and then in a multi-year effort, standards were selected. In a little bit of contrast to these standardization efforts, we have projects that we call of a more exploratory nature, and these include the privacy-enhancing crypto and the multi-party threshold cryptography efforts. It doesn't mean that we, certainly there will be standards in the future, but we realize a number of challenges, namely what we sometimes call the combinatorial challenge of, number of system models, number of parties, number of communication assumptions. So there are many possibilities, and so we think that there is an advantage in doing a slower process. And what I will talk about, especially in the second part of this presentation, is of exactly a public call that will not be similar to the standardization processes, but will seek to collect a body of reference material. In any case, a key takeaway here is that there is really a vast area for developments in both standardization and exploratory projects, but as I mentioned, I will now focus more on the exploratory side. Okay, so that was it about the NIST generic intro. Now I want to take the chance to disseminate a little bit what we do with multi-party threshold cryptography. So for those who might not be familiar with the term, so the scope of threshold cryptography is actually cryptographic primitives in themselves. So for example, signing, encryption, key generation, etc. And what we want here is to have a threshold way, a threshold scheme of implementing these primitives. Okay, what do we mean by this? We mean that when a secret key is used, we want to split that key, the technical term is secret share, and then we split it across multiple parties so that no single party knows the key. And then we use multi-party computation to perform the needed operation. So if you will, threshold cryptography is kind of MPC applied to cryptographic primitives. Why do we call this a threshold scheme? It's kind of a strange name. Well, because we say that the operation that we want to perform is secure as long as the number of corrupted parties does not exceed a given threshold, in this case a corruption threshold. And what we achieve with this is that we achieve a decentralized trust about the key, about the operation of the key, which does never need to be reconstructed. So you effectively, not only do you split the key, you then are able to obtain the intended output, let's say a signature, without ever recombining the key, and so this is a way of avoiding single points of failure. Okay, so what is the NIST call for multi-party threshold schemes? This is the main initiative we have currently within this project. It's a public call for input to form a body of reference material. And so, you know, it deals with threshold schemes, and just to use a little pun here, it stands at the threshold of advanced cryptography. It's our way of entering this field. So this fits in the reference materials approach of these exploratory projects, both of the PEC and the MPTC projects. And important to mention, because this has been a difficult message to percolate through the community, because especially the PQC project had so much weight that people just expect, because we're doing a new call, that, oh, you're about to standardize threshold schemes. Hold on a little bit. This is not a competition for selecting a standard. This is a process where we're making a call. We're hoping for submissions. We're going to post the submissions that we receive. That will be the subject of a public analysis. And then what we're promising at this point is that we will do a report about what we receive, and that will inform subsequent processes. Okay, so the call is organized into two classes. The first one is for NIST standardized primitives. So we're looking for the public, you know, the cryptography community of experts to propose what are the best threshold schemes to implement NIST standardized primitives. That includes signatures, public key encryption, symmetric key primitives, and key generation. We have a second class for special other types of primitives, and notably, these include not only the signatures, public key encryption, symmetric keys, encryption, and key generation. It also includes fully homomorphic encryption and zero-knowledge proof of knowledge, and also what we call gadgets, which are basically building blocks that can be used across a number of primitives. One of the reasons why we decided to put in these two kind of different primitives, FHE and zero-knowledge proof of knowledge, is because we recognize their increasing relevance. And if we're doing a process that has such a high cost of, you know, analysis, public engagement, and all of that, we felt that it would be an advantage to include these two categories as well. So here's just a little bit of table, you know, just in case you want to peruse this later on. Phases and deadlines, you know, let's call phase 0 just for the sake of this presentation, is actually getting the call out. We had the first public draft in 2023. The second public draft was out in March of this year, and we expect to have the final version in a few months. Although I've been learning with this process that it's very easy to fail predictions of timelines, but we know we are much closer to the end than we were in 2023. Once we publish this at time x0, then the first phase will be a phase of previews. Because this is not a standard competition, we actually want the world to be aware of what teams are preparing. And so we strongly encourage teams that want to do submissions to present a preview, basically a plan of what they want to submit, and there are going to be two opportunities for this, 2 months after the
the call is published, and 3 months later on. And only then do we get to the phase of submission of packages, and essentially at least 8 months after the final version of the call is ready will be the deadline for regular submissions. And then finally, we'll have a period of analysis for public presentations, package updates, and eventually the report. Roughly speaking, the public presentations of the submissions will happen in 2026. We expect to have a first report around 2027. Just a few other notes on exploratory activities of interest to the public. We expect to have multi-party threshold schemes workshop still this year, October or November. It's starting to get more likely that it will be in November. We will try to coincide this with the first preview phase. So we will actually have a session where teams will present what they intend to submit to the threshold call several months later. We also have the PEC project, which I haven't spoken much about, but just to quickly mention, the goal of this project is to accompany the progress of emerging privacy-enhancing cryptography, and in scope are many types of primitives, including multi-party computation, fully homomorphic encryption, zero-knowledge proofs, private set intersection, private information retrieval, special types of signatures, and others. And we also host a seminar series called Special Topics on Privacy-Enhancing Cryptography. And one of the things we appreciate in this project is that all the information that we collect is part of the public domain. So everything is published. And also, if you're interested in actual reference material, we also had some past events, including a workshop on privacy-enhancing cryptography last September. We also had a previous multi-party threshold schemes workshop in 2023. And we host also a diverse set of talks, for example, at the NIST Crypto Reading Club. This is virtual these days, so you can actually subscribe to attend the talks. Okay, so this was kind of my job in terms of disseminating these ideas. We hope people in this room are interested in this. If not for submissions, then for the subsequent process of analysis. By the way, I forgot to mention, it was in some slide. Okay, here it is on the top right. Public comments, by the way, on the second public draft are due on May 30th. So you can actually still provide public comments, and we really appreciate any feedback you may have. Okay, some thoughts. I actually want to start with an analogy. Actually, this is a fun construction at the NIST campus in Maryland. So this is the NIST stone test wall, which was constructed in 1948 to study the performance of stone subjected to weathering. And it's still standing there. And if you actually go close to there, so this is a wall that was built with several thousand little stones. And if you go there today, you can see that some of them have eroded, others, in very bad shape, and others are still good. And this is kind of a nice analogy to ask the same about crypto building blocks, namely taking in consideration the topic of today's event, right, of future cryptography. So imagine what is it that will remain valid in 75 years from now, for example, in terms of crypto standards? We already have a hint that probably pre-quantum standards will not be, or quantum vulnerable standards will not be here anymore, assuming that we'll have a quantum computer. But we can also ask which new blocks should we actually develop and standardize to enable a good crypto wall that will still be standing 75 years from now. And also, once we actually get into crypto threshold schemes, which kinds of walls, meaning which kinds of complex compositions, can we actually safely create out of building blocks? And just to kind of finalize the analogy, because this was performance of stone subject to weathering, you can also ask, what is the kind of crypto weather that we need to be prepared for? Understand this as like what kinds of attacks or adversarial scenarios. Okay, so now I get to the point of kind of doing a few assorted notes based on experience or past research. One that I find very interesting that I think is often overlooked is the actual characterization of reliability of long-lived threshold schemes. We typically have the understanding, okay, if we have a threshold scheme, we're definitely better because we no longer have a single point of failure. Well, turns out that depending on the parameters and the mission time, we're sometimes actually also increasing the surface of attack. So the keynote I want to leave here is that it's actually relevant to look at the model of intrusion to figure out if a scheme that has multiple parties is actually better than one with just one party. I took a few snapshots here from an older paper that basically shows the transitions between states, healthy to intruded and then back to recovery state. And if you actually start characterizing how these transitions happen, you can actually figure out some scenarios where the threshold scheme might actually be worse. But there's a mitigation. You can implement recovery of nodes as a way of if you parameterize it properly, then you can get a better scheme. Trust versus trustworthiness. We've heard these two words today already. I think this is also a very important aspect. It's important to match trust with trustworthiness. And sometimes the terms are used interchangeably, even though they may mean different things. So I just sort of putting here two thoughts on how sometimes we can match this if we're starting from a point where where we're relying more on trust than trustworthiness. Well, sometimes we can do clever use of cryptography to decrease the trust requirements. For example, if we use MPC, zero knowledge proofs of FHE, we can actually reduce the trust that we need to put in some parties, maybe because we're no longer sharing private data. And then in other cases, and I think this is more to the topic of today's event, we can also increase trustworthiness via, for example, a standardization process that is highly open to public scrutiny and where we try to verify specifications. And then, again, this is not my topic of expertise, but that's the topic we've been hearing all along today, by validation and certification. So hopefully there is a good side on trust and trustworthiness to try to level them one to the other. Just a few brief notes before finishing and leaving time for questions. So we care about what we sometimes call known answer tests, or AKA test vectors. When we deal with threshold schemes, some challenges arise, and I think these are interesting challenges for people who are interested in certification. How do you deal with non-determinism in distributed systems when you can actually not control the order of messages and other aspects? Floating point operations, even when you're dealing with a single party, if you're compiling your code across different machines or using different compilation flags, optimizations, or different processors, you actually usually will get different results. So this idea of test vectors, it's not so straightforward to implement. And this is actually a challenge that we think we're going to have some nice discussion in our threshold call. And then by the own nature of threshold schemes, we have this issue of a combinatorial explosion of parameterization. So it's actually difficult to look at everything. Also, just a final note on quantum vulnerable versus quantum resistant solutions. The threshold call is actually opened to both, notwithstanding that there is an envisioned deprecation of quantum vulnerable schemes by 2035. And one of the key insights is that quantum vulnerable crypto has very good references for what we would like to achieve in quantum resistant crypto, which we might not yet be able to, we might not yet know how to do at some point. And also there's an interesting question of, might there be cases in the future where we can still use quantum vulnerable crypto? Maybe not for encryption, because we have the harvest now, decrypt later attack, but maybe for authentication. Maybe in a protocol where you only need to have an RSA key not broken in 1 minute. If 10 years from now the quantum computers, if they are here, they take 1 year to break an RSA key, there might still be a few use cases. Some concluding remarks, and I think I will still leave some time for question. Again, some assorted remarks. When we deal with advanced crypto, at least the experience I've been having in terms of reflecting on this is that we actually need to develop advanced processes for standardization or certification. And in a sense, the threshold call is the result of that. It's kind of a customized process that relates to the difficulties we've been finding of realizing that it's not the same as just going for post-quantum crypto and standardizing a signature. So the threshold call is an approach for exploring advanced cryptography prior to reaching standards. Our aim is to eventually develop recommendations about advanced cryptography, which will support future processes. There's definitely an ample room for participation. I would even say it's essential, the public participation. I'd like to mention that in kind of my personal opinion, I think privacy-preserving applications are a key space for adoption of future crypto. There are certainly other cases, key management, etc. But privacy-preserving applications have a lot of room for adoption of future cryptography. And as a final note, again, please pay attention, stay tuned to MPTS 2025. You're welcome to participate to hear or speak thorough elaborations about our notes on advanced cryptography. Thank you so much for your attention, and I'm glad to take questions.
There's a whole 7 minutes for your questions. Petr, please.
Thank you very much for the talk. I wanted to ask on the status of Frost standardization, because my perception was that with the Frost algorithm, there was something moving forward more than exploratory.
So my knowledge is that there is a Frost IETF standard at this point, but the actual threshold call at NIST is not open. So we actually welcome that a submission of Frost, that Frost is submitted to the NIST call so that we can analyze it. We've actually done quite a bit of research on security formulations and security properties of threshold signatures. So we are aware of significant differences between different threshold schemes for cryptographic primitives. Just as an example, Frost is heavily focused on achieving the lowest possible number of rounds, so 2 rounds. As a result, they actually have this property where the so-called rushing adversary, the adversary that waits to be the last one to talk, can actually bias the result of a public signature. That does not affect enforgeability, which is kind of the quintessential property of a threshold signature, but it may allow for some, let's say, covered channels or things like that. So there's another trend that goes more in the realm of 3 rounds that tries to achieve simulatable security, and so it has different types of guarantees.
Thank you very much. And while I have Mike, I would like to ask, the Frost is coming from the pre-quantum world, right? So are there any requirements that things are supposed to be post-quantum secure, or not really?
No, the call is open to pre-quantum. We actually don't have that many requirements in terms of security formulation. Apart from, we want implementations to target at least a 128-bit security level, or level 1 in the PQC setting. And one very strategic decision, we require the threshold schemes to be actively secure. Meaning, maybe for the people who are not familiar with MPC, that means they should be resistant against an adversary that can corrupt parties maliciously.
Thank you very much.
You're welcome.
Can I have a mic in the front? Here, yes.
So if I understand correctly, this idea of public call is to use public global talent for solving those challenges.
You said global talent?
To use a global talent to challenge those, to address those challenges, right? You have in NIST. So my question is, do, for example, teams from China or Iran also contribute to solutions?
So at this point, the call is open. It's a public call. It's in the public domain. So we're open to receiving submissions from whoever.
Practically, there are cases when Chinese guys and Iranian guys who are not always friends, they also just do some stuff for NIST.
I don't know of any restriction with respect to the threshold call. So as far as I know, the call is open to the public.
Okay. Daniel?
So thanks. So it's really nice to hear that NIST is now doing these more experimental things, because historically NIST has always been super stringent on everything cryptography. So for example, when ANSI says that use these technologies and this is very flexible for other countries, as you mentioned, many players just take NIST standards, even if it's not mandated for them, and follow them. So why so late?
Come again?
Like why is this happening so late? Why the shift these days? Yeah.
Well, I mean, it's a very interesting question, but I should say that we get both sides of the question. Some people are like, oh, maybe it's too soon. Why are you standardizing right away? So the way we're seeing, we're not standardizing right away, so it's not too soon. The being too late, I would say, one of the slides that I often use in these presentations for intro to NIST, I had to trim quite a number of slides, is like an organogram of the NIST, human resources. And a real challenge is like human resources. Is like how much people are actually working on this thing. So this is happening now because there's somebody working on this now. Me being one of the persons. Should this have been done before? Maybe if there were more people working on it. As I mentioned earlier on, my background is an MPC. I did that as a PhD student, and when I joined NIST, part of my vision and interest was actually to go to NIST and somehow promote MPC, and that's part of the effort I've been doing. So I would say, I think this really applies across the board, companies or governments or institution-like standardization bodies. There needs to be people behind an effort to make things happen.
Right, thanks.
I hope that kind of addressed the question.
There's room for one last question. Nikita has one.
So you covered about passive and active corruptions, but also interested, will you accept covert corruptions, like as opposite to active in a submission? And what about static and versus dynamic corruptions? Does the scheme need to be dynamically secure against dynamic corruptions?
The scheme does not need, just to make sure we're on the same page, by dynamic you mean changing number of parties?
No.
I mean, do you mean adaptive?
Adaptive. Oh, sorry. Yes, adaptive. Yeah.
Okay.
But I mean that like adversary could change which parties they corrupt after the keys are generated.
It's a very interesting point, namely from a theoretical perspective, and we devote part of the call to explain that. And actually, after we published the second public draft, we already, by the way, there's an MPTC project link here where you can find information about the MPTC forum. We actually already published a clarification exactly about that because we realized it was a bit strange. So if I can spend, I guess, a minute in this answer. So it is well known that proving adaptive security can be extremely difficult depending on the security formulation. However, we certainly don't want a scheme, let's say pick a threshold signature, that would become suddenly forgeable if you have an adaptive adversary. So the way we encode this in the call is to say the following. Active security versus passive is really a requirement, and we need a proof of security for that. With respect to static versus adaptive, because we recognize the difficulty, what we're asking for is a technical argument that the scheme does not break down with respect to the critical safety properties if the adversary suddenly becomes adaptive. But we don't require a proof of security in a security formulation that would actually be too strong. Maybe for the people who are technical in the area, we don't want people to start using, let's say, deniable encryption and things like that just to achieve adaptive security, which would be totally overkill. We actually expect this aspect of adaptive security to be a nice discussion topic as part of the analysis of the schemes, and in fact we're expecting to have a session related to that in our MPTS 2025 scheme.
Thank you.
You're welcome.
Thank you very much. There's going to be a networking break for the rest of the discussion. Let's thank the speaker again.
Thank you very much.
If I may, thank you very much. I didn't make slides for the concluding words. First of all, I'll clear up something that I was noted about. In Kristjan's talk, when we talk about human resources, and I was so glad to hear that US also has a problem with human resources. It was made my heart sing. Cryptographer is a very complex definition. So yes, in that study, in this first phase, to create the evaluation capability, we looked at people who have published or been an author in a cryptography paper. This is not the absolute basic need if you want to do certification or something like that. However, what I'm arguing is that the number of people who can do the additional things needed might not be too much larger, twice possibly, 2.5 times larger maybe. So still the question is sustainability. And as Luís said, you need someone with a mission to carry something forward. So there needs to be someone with a mission to carry this torch forward also in Estonia. So the question is that whose responsibility is it? And if given that we are organized as a very free nation, free state, then people can indeed choose in the universities what they are going to study. But the question is exactly that for certain questions of sovereignty, whether digital or otherwise, there needs to be a program to support that. Now, I cannot be sure, but based on hearsay, the coalition treaty of the new government that has been working for a few months already will include a sentence that says that there will be increased study positions for certain areas, most likely AI. But there is a chance, and we have asked the right people, there would be a bit of a carve-out for cybersecurity and cryptography PhD positions as well. So maybe in 5 years, the first people who can do that will come out of that new program. And I believe that today what we achieved was we achieved a body of knowledge, much like what NIST is doing with threshold code. So no standard yet, but a body of knowledge, so that if future generations come and see and they start reinventing some of the wheels, they see that, there is this curated body of knowledge collected from across the planet, and it is now here, and this is our baseline we're building on top of this. So that's a very good point. And yeah, I do believe that Estonia will continue to be on the forefront of deploying some of these things, because it's slightly easier at our scale. Thank you very much, everyone. It has been an absolute pleasure being with you here today. We were on time, and I don't have a desperate need of doing this for too long. So I think there's still time for discussions, and hope if there's a good topic, then see you next year again. Thank you. Birgit made most of the logistics happen, so let's thank her.